Welcome to today's workshop. This is the Introduction to Data Science for Environmental Scientists. My name is Jing Liu. I'm the Managing Director of the Michigan Institute for Data Science, or MIDAS, which is the unit that organizes today's workshop. I want to, first of all, I can't advance my slide. Yes, I can now. First of all, I want to thank Yang Chen and Jonathan Gryak for their work to put this event together, and also the other presenters that you will hear later today. Really appreciate all the effort all of you put in this. But I want to say a few words about MIDAS and to give you a context of this event, and also what else you might find useful looking forward to do data science research in your own domain. Okay, so MIDAS is a campus-wide organization. Our central goal is really to enhance the data science and AI research capacity and support the research effort of faculty and campus organizations and trainees as well. Interesting facts. We are the largest data science institute at a U.S. university based on the number of faculty affiliates, and we're one of the most scientifically diverse as well. This actually is useful information as we talk about what we do and how we would like to work with you. So who we are, our faculty affiliates come from every school and college at the Ann Arbor campus, plus Dearborn and Flint. And we have about 450 faculty members right now. Also in our community are more than 1,000 students at both the undergrad and graduate level. We also have a new staff collective for Data Science Network. So what we do, I would like to think about 3 buckets for what we do: research, training, and collaboration. I will go to a little bit of detail for each of these. For research, though, it's mostly about enabling groundbreaking research for both methodology and application, but also leading the effort on campus to enable ethical and reproducible data science and AI research. So I'm going to show you here our role as a research enabler. So our faculty members, because of their diverse scientific background, they are a really great community in terms of forming interdisciplinary research to both advance methodology and also apply such methodology in every application domain. So MIDAS organizes research incubation events. We provide pilot funding. We provide access to important data sets. And one thing we're developing now is more support for grant proposals. So through such efforts, we are able to, in the past 6 years, we were able to enable more than 130 grant awards. External grant awards with a total amount of more than $100 million. So training is something that we started recently, but it's becoming more and more systematic. So the event that you're attending today is part of the more systematic, intense, and also the beginning of a more intensive training program. So our intensive training program tends to have 3 phases. One is a short workshop, and followed by an intensive bootcamp, then followed by workshops to support grant proposals of the attendees. We ran the first such sequence last year for biomedical researchers, which will be repeated this year. And today is the first phase of the training event for environmental researchers, and more are in the planning phase for other domains as well. We also offer short workshops And these are often organized by our own faculty members. They can be cutting edge methodology. They can be introducing specific tools, and they can be teaching people how to start using a particular data set for research. Faculty members who are here in this meeting may also have students and postdocs who want to be involved in data science. And some of the attendees today are students and postdocs. I want to mention some ways that you can be involved. We have a 2-year Michigan Data Science Fellows postdoc program with faculty members as co-mentors. This program has been around for 3 years now. We also have a graduate data science certificate program that is open to all U of M graduate students. Students who are not in these programs are connected with MIDAS through various ways. We help faculty members connect with students who can be their research assistants. There are a number of data science and AI student clubs on campus that MIDAS provides mentoring for. We periodically organize data competitions and connect students with projects that really serve the community through data science and AI expertise. I just want to quickly mention, we also help faculty, researchers, students, and campus units form collaboration with external partners, both the private and the public sector. So I want to mention, if you read our announcements for fellowship program, pilot funding program, you'll notice we mentioned a lot that we want to primarily focus our resource on research in 4 pillars. So I just want to mention here what they are. The 4 pillars really are responsible data science and AI, and that's the first pillar. The second one is enabling the use of novel data types. Currently, we're focusing on data types that enable novel social science research, but the focus will evolve. Third pillar is enabling the adoption of cutting-edge data analytics. Right now, we're focusing analytics that benefits health intervention research. And again, this will evolve over time. And the fourth one is new strength, national priorities, U of M strength that can be boosted significantly through data science and AI. So meanwhile, while we support these pillars, we also will continue to support an inclusive research community, foster collaborations, and promote methodology development. So I want to end my introduction by mentioning a few things that are coming up that some of the attendees might be interested. Our pilot funding program, if you're hearing about this for the first time today, it's actually already too late. But on March 23rd, we will offer a PODS awardees showcase that features the awardees of the last round of the PODS program. Michigan Data Science Fellows postdoc application is due in 4 weeks. We're seeking from all faculty members colloquial proposals for the fall of 2022. We will offer a mini symposium on responsible data science and AI on April 6th. And we'll let you know more about new research and training activities within the pillars. So now with that, I'm going to pass it to Jonathan, who will introduce today's training content. I'm going to stop sharing. Okay, Jonathan.
Well, thank you so much, Jing. Again, welcome everyone to the workshop. My name is Jonathan Gryak. I'm a senior scientist from MIDAS. Let me just get my slides up here and we can get started. Hopefully this will be the right one. Okay, so can everyone see my slides? Okay, so today I'm going to be going over sort of the training program overall. Again, as this is just a workshop, the first part of it, and I want to emphasize some of the aspects of the training program who can benefit, who maybe this isn't for, as well as I will talk a little bit about some of the potential applications of data science, environmental science as well. So just a reminder of today's agenda. So this is right now the talk at 12:15, and then later we'll have the other lead trainer, who is Yang. She'll be talking about sort of the differences and similarities between data science, machine learning, and understanding when to use certain techniques and when perhaps not to. We have a great slate of panelists from all different departments to talk about their own research and how they are using data science techniques in research applications related to environmental science. And I will end with a description of the next steps of the training program. We'll have the Q&A, and then we'll have just a open discussion at the end of the workshop. Okay. And so what are the goals of the training program? So there's twofold. One is to provide researchers with the sort of requisite training to successfully apply data science techniques to environmental science research questions. So again, this is primarily a training component, and then most of that will be done in the boot camp, although we'll have some hopefully whet people's appetites today with some of the things that I presented. And to that end, also what we want to try to do is develop a research community across the university that will advance the application of data science to these domains. And when I say environmental science, we mean this in a very inclusive sense. Okay, so this includes people who are working in environmental science proper. It could be climate science, earth science, or ecology. Again, we have representatives and speakers today from a whole host of departments and schools, Cs, earth and environmental science, evolutionary and biology and ecology, as well as climate and space science. So this is a broad group of people. And so we mean to be, again, inclusive. Everyone who thinks they work in this space and want to learn about how they can utilize data science for their research are welcome to participate in the program. So the program, as Jing mentioned, has 3 components. So today is the workshop. We will have a data science bootcamp that's currently scheduled for May 16th to 20th, but that will be firmed up shortly. And then we will plan on having some follow-up sessions, one each semester next year, in order to sort of try to keep the community going and provide more opportunities for collaboration. So why should we, if you're working in environmental science, again, defined broadly, why should you consider data science and data science tools for your research? So, there are huge amounts of environmental data of all different kinds being produced for all sorts of applications. So just one very simple example, which is relatively small, is this data set from NASA, which is the WorldView data set. It's a whole bunch of different types of satellite images. This has 450 terabytes of data, and they have available through NASA and climate.gov, other online websites. There's petabytes and petabytes of data that are available for analysis. So we can't be expected as individuals, to analyze all this data through some kind of, manual means. Another thing that's important to realize is that, even though many of these phenomena do have known mechanistic models, or models of the physical processes that you can use, they're usually too computationally expensive to include. So one example would be if you wanted to model, aerosols or clouds in the global environment, those models are too expensive to utilize, directly in a model. So, however, one of the nice things is that many machine learning models, as you will learn about over the talk and hopefully in the future, they don't have such restrictions. And so this is one potential main advantage of using data science techniques here. Another thing to think about is that the types of data and the modalities of data that we're thinking about, they are diverse and they also have kinds of information in them, which is very complicated. So we have videos or images. We have different kinds of signals. In this case, this is a seismogram. We have all kinds of sensor networks throughout the world, whether it's measuring climates, migration of animals, ocean temperature. And we also have a whole bunch of sort of either chemical or genomic data. Again, each of these is its own complex type of data. And again, we, in traditional methods, trying to think about, reasoning from first principles about how to potentially get information out of this may not be feasible. So this is another case where using data-driven techniques can be helpful. So maybe it'd be helpful to step back and just say what we mean by data science. What are we talking about? So this is one definition from the NIH. And so it's interdisciplinary field in which quantitative analytical approaches are developed and used to extract knowledge and insights. Right? So there's this lovely diagram here of seeing sort of how the different kinds of both domain knowledge and information come together to sort of make data science. So again, we have actual computer science or things from information theory. We have the actual domain research, the disciplinary research, and we have tools and techniques for math and statistics. And these are all form sort of the core of data science, and it includes things like machine learning or informatics, AI. And again, machine learning by itself is just a subset of broader artificial intelligence techniques. And oftentimes in an application, it's not that you use just machine learning or just AI or just statistical techniques. You may use a combination of them, and there's a lot of power in combining different classes of techniques together to help solve your problem. So what are the skills that you need in order to use data science in your research? So obviously there is some knowledge of mathematics, although again, if you're utilizing or applying these techniques, you don't have to you don't have to be a mathematician, but you do need to have some basic facility with mathematics, some calculus so you can understand optimization. Linear algebra underpins many of the machine learning applications, and as people who work in mechanistic models, that's also the case in developing systems of equations. Some statistics and probability as well, and also some programming too. I think this is becoming a lower and lower bar as time goes on, as machine learning and other techniques become more widespread. There are a lot of great libraries that really take out the pain of having to be very skilled in programming in order to do your analysis. So there's lots of great frameworks available to help you with that. So, but the thing that even if you are not working in this space, something that's important to remember is that, or another skill you can gain from this, is the ability to look at some other results and determine whether or not you should buy what people are selling. So there are a lot of times, especially, I'm also a faculty in medical school, and you can look at papers in which people, sort of blithely, apply machine learning to some problem, and you realize that, the data wasn't properly separated. There's data leakage, or patients appear and were used that were double dipped in some way, that they were used both for training and testing or other kinds of things. And so the ability to understand, how you put these models together will enable you to improve your, ability to analyze results from other papers and so forth. So who may not want to come to this training? So I mean, I know people are coming to the workshop, so that's great. But if you have had prior trainings in AI or machine learning in the past, then this may not be for you. You might get bored, because again, this is supposed to be more for an introduction and making sure people get a set of basic skills that come with it, right? So we aren't necessarily going to give you the latest and greatest models, but there will be a lot of current techniques which are perfectly valuable. If you aren't planning on, maybe your work doesn't have as much of a quantitative aspect to it, or you have statistical or mechanistic models or analyses that you are comfortable with and they work for your application, then this again may not be necessary. It is not the case that you need to use machine learning or AI for anything. It does not supplant existing modes of analysis. Okay, it's just as said. So who may benefit? So if you, again, have some basic math background, and you want to understand AI and machine learning and more broadly, then I think this would be a good program for you. Again, in the training that we did last time for biomedical scientists, most people only had a basic statistical background, but we provide all of the, the basic, additional math pieces that are needed in context to help you understand the models that we're retraining or using. So again, this training and being able to be fluent in sort of the terminology, what is cross-validation, what is, what are the metrics that are used to evaluate models. These will be helpful for everyone as a scientist to be able to understand results from data science and again, be able to communicate with each other. Again, if you are, there's a broad group of people here. We have graduate students, up to full professors. So, but if you want to include data science as part of your research, and then this training program, again, I think would be beneficial for you to sort of have a basis from which you can then determine which aspects you may need to learn more for your particular application, or which techniques you may need to gain a better understanding of. This will serve as a basis for you to continue developing your own skills for your own research purposes. Okay. So one thing, as I just mentioned, is that what you need, this machine learning and AI, they're not magic. They're not suited for all applications. So it's important to know when and when not you should use AI or machine learning for your work. Again, I think that having this training afterwards, you'll be able to better understand how these techniques are used, when they should and not be used, again, and be able to communicate with others who work in this space. And for those who are either early career postdocs or trainees, you'll be able to use the skills that you develop in this training workshop to be able, the training program, to include data science ideas into your proposals. And then this is something that, as I'll mention later, the follow-up sessions are expressly to try to help you develop your ideas and potentially give you guidance on how you can use data science, in proposals for yourself. So. We will also gain some programming experience. We'll have a set of labs that are in the bootcamp that will give you some hands-on experience, using or building machine learning methods. Again, this will be in a sort of structured environment. There's at least in the past, we've used this framework known as Jupyter Notebooks, which makes it relatively easy for you to be able to take a piece of code, modify it, and not get stuck up in just all the minutiae of programming and be able to build these models even with limited experience. So what are things that are not included in this? So again, this is not going to be a training in statistical or mechanistic methods. There's other courses, and we assume that people who are coming from environmental science broadly have either training in mechanistic models or some training in statistics, so that won't be included. We won't be able to cover everything. Even in a week boot camp, there's only so much that we can cover. So we want to, mostly deal with, give you, again, a conceptual understanding of how these work. You will still be able to, again, explore and play with individual models that we present. But we want you to be able to do that without knowing, all the details of the mathematics about how these particular models work, or, without having to really become an expert in machine learning or AI. Again, to that end, we don't expect people who come out of this training to also be able to develop their own methods. Again, there are a lot of models which exist now, and again, there's different methods that can work for almost any kind of application, whether it's time series, forecasting, classification, anomaly detection, you name it. And so just knowing the methods, knowing how to use them, knowing how to modify parameters of existing methods to suit your application, that will be sufficient for most of you in applying data science to your own research. You don't necessarily have to develop a new method. Okay. And similarly, the coding that will be done, it'll be, again, using libraries so that you don't have to write from scratch sort of machine learning algorithms. Okay. All right. And so I wanted to just briefly provide some overview of a couple different kinds, a couple different current applications of data science. Again, we're going to see a lot more of these, in the talks this afternoon from the other faculty who are here. But this is a diagram from a survey paper from Zhang, who sort of showed roughly sort of how people are using different kinds of machine learning techniques in environmental science. This one was more related to more environmental science, as well as sort of different kinds of chemical things, environmental quality, and so forth. So, but none of this is specific to environmental science. These are things that can be done in general with machine learning techniques. So again, on the left, you have different kinds of data formats that could potentially be analyzed by machine learning methods. So that could be tabular data, it could be images, it could be graphs, right? It could be a network, or it could be a molecular structure that's represented as a graph. And of course, any kind of text. It could be, genomic information. So almost any kind of data could potentially be that, as long as it can be digitized, you can utilize it in machine learning model. Okay? And so again, we roughly see sort of the sort of pipeline of what happens in machine learning. You have data, somehow it is captured, transformed, it is input into some kind of model, right? And then there's an output of that model, right? And then there's many different kind of models that do different types of things to the data. So in some cases, it is going to look at prediction. So we see on the right here, there's what looks like some kind of linear regression of points, or it could be looking at clusters, trying to determine which data points are similar or dissimilar to each other. One of the things that you can do also with machine learning models is that you can sort of interpret by creating a model that predicts or classifies some data well. You are able to interpret those results, and there's different methods to doing that. Some models are easier than others, but there are a whole host of methods to try to interpret either how the model is making its prediction, and consequently what are the particular features, what aspects of the data are leading to, or the most important or relevant to making a prediction or classification. So in this example, so some of the things that you can use it for, as I said, you can make predictions. You could be looking at determining which of the aspects of your data are most important. You could detect anomalies, which of these points are not like the others. Or it could also, that's also considered rare event detection. It's another way of thinking about anomalies. And you can also use it for actual discovery. In the case of, I said this is from a chemical journal, but this is looking at trying to determine, new materials or chemicals related to, say, toxins in the environment and so forth. But again, this is a broad sort of, sort of sense of what sort of is possible with machine learning. So I just want to provide a few different examples of current applications. Again, we have a broad view of what's included in environmental science, but here are a few different ones that have been well established. So this is an example from Hugh, who they predicted particulate matter in the continental US, and they utilized a random forest model, which is a type of supervised learning model. And in this case, supervised learning means that I have a set of inputs and outputs, and I want to learn a function that will be able to tell me when I have new data I haven't seen before. I input that, it will give me an output. And again, that output could be predicting, in this case, the particulate matter concentrations. It could be making a classification, but supervised learning is about having a set of labeled examples of inputs and outputs and learning some mapping from inputs and outputs that works well and generalizes well on unseen data. Another example, this paper from Gagne et al. And this again also used a random forest model. It's a popular model. It's been around for quite a while to predict sort of extreme hail events, within existing weather models. We also have another example of prediction, but this case is looking at chemical toxicity. And this is not supervised learning. This is unsupervised learning. This uses a method called k-nearest neighbors, which is basically trying to look at data points and some kind of information about them and trying to cluster them into different groups. So in this case, trying to look at these certain chemical compounds and be able to predict, even if I don't know if this compound is carcinogenic or not, based upon its similarity to other compounds, can I make such a prediction? And so they did this for about 275 compounds and made these predictions using this method. Another example was looking at for feature importance, and this paper from Bagari utilized an artificial neural network, which is just another kind of supervised learning model. So again, this is still looking at inputs to outputs, trying to be able to make learner function that will given a new inputs, will tell me what the output is. But an artificial neural network is just another type of model. It's another type of sort of mathematical formulation that enables me to learn this mapping. In this case, they use this network to predict whether or not a certain kind of plants would be able to pick up or environmental contaminants. And then they analyze that model to then figure out which of the chemical properties. I think they looked at strength of hydrogen bonds and some other kinds of aspects of the molecules themselves. Which of these was the most predictive of uptake? And so again, this is where you can not only utilize a model to give you a prediction or a forecast or a label or classification, but also by interpreting and understanding how the model is making its decisions, it can give you insight into the actual input data itself. In this case, the data related to environmental contaminants. And this paper from Diary utilized two different models together. So it used what is known as a recurrent neural network. And this is a type of reinforcement learning, which is another kind of machine learning. Again, reinforcement learning in this case is you say, I don't tell a model what is right or wrong, but I give it a goal. I say, I want you to, maximize, the amount of money you're going to make, by making it a trade or something like that. And the model will take actions, and then it will get feedback. Did I make money? Did I lose money? And it will use that to then change the decisions that it's going to make in the future. So a recurrent neural network is one type of reinforcement learning. So in this problem, they utilized, in this paper, they utilized a RNN along with what's known as a one-class support vector machine, which is another type of unsupervised learning. So a type of clustering, where I don't give it labels, I just try to find similarities between my data. So they combine these two models together to be able to detect abnormal levels of sort of water coming into a wastewater, treatment system. And this is an example of where it's not just that one model may tell you, what you need or solve your problem. Oftentimes you can utilize multiple methods, either sequentially or in parallel, to be able to solve your problem. So these are just some examples of ways in which data science techniques and machine learning techniques have been applied to environmental science applications. There's a couple of emerging trends that I wanted to discuss. I'll just give two different examples. And one is this idea of equation or model discovery. So again, many people in these domains utilize mechanistic models. They have models which are systems of ODEs or PDEs, and they're used to using different kinds of numerical methods to simulate those and do approximations on sort of parallel computers. But in some cases, you don't necessarily know what the model itself is or what equations govern some kind of process. And so people have been utilizing, by collecting data people have been able to utilize data to try to determine the set of equations or system of equations that best models that data. So one example of that is this paper from both that they created a machine learning pipeline. I think it's called DeepMod. And this uses an artificial neural network to learn systems of PDEs. And the other piece that was neat about this is that they tried to add different amounts of noise to the data points that they had. And even in high noise situations, at least for the examples that they tested, like they looked at, I think, some kind of diffusion of certain kinds of proteins and gel, as well as a few other kind of smaller examples. But they were able to learn a system of PDEs just from data, even with noise, and using something like on the order of 100 samples. So this is one example of where you can take data, and this is one method by which you can take data and then actually learn, like again, in this case, a set of partial differential equations. Another area that people are, that's more recently people have been using, are applying a data science, environmental science, is the use of generative adversarial networks for data augmentation. So GANs are just a type of generative model, meaning that they not just make a label, but they actually they learn some kind of, say, distribution on data. They somehow learn the essence of the input data so that they could generate samples of data that are very similar to the inputs. And GANs in particular utilize a couple different kinds of neural networks together in order to be able to sort of make this generative model. So in the context of environmental science, people have been using this for a couple different areas. One of them is sort of upsampling data. So what you could do is take, for instance, for climate data, you have a very rough grid that is, you have sensors, say, around the globe, say, looking at air quality or something like that. So it's very coarse. And so people have used GANs to be able to take this coarse, approximation of, say, of this data, and then be able to sort of smooth, and generate data to fill in those gaps. Another example is this paper, which is from Wong, and they looked at irradiance data because they wanted to do power forecasting for solar cells, and wanted to be able to determine the level of irradiance to make these predictions. But irradiance varies by weather, and so what they were able to do is for different weather types, they made a GAN that was able to synthesize what the irradiance should be for all these different types of weather. I think it was initially 30 types that they looked at, and then they used the output of that as an input into a forecasting model. So again, this is another example of a combination of multiple models to be able to solve the problem. And so with that, I think I will stop here. We have a couple of minutes if anyone has any questions. I'm happy to answer them, and then we'll move on to the next step afterwards.
Hello, can you hear me?
Yes, I can.
Okay, good.
You can see your presentation as well.
Okay, good. So today I'll talk about data science methods for environmental science from a statistician's perspective, because as myself, I'm from the Department of Statistics. My talk won't be very long. So people have been asking this question, even within the field of statistics, people have been trying to understand what is data science and what is the relationship between data science, machine learning, statistics, and other related fields. And through different kinds of social media and different academic journals, you will see a lot of pictures like this. I'm just digging out two of them as just the examples. I'm pretty sure you have seen this diagram on the left-hand side. Essentially, people say data science is between the intersection of computer science, mathematics and statistics, and domain knowledge. And people have been trying to develop data science methods based on the intersection of computer science, math and statistics, and domain and business knowledge. I think this data science is like a big topic, and I think myself is too junior as a position to comment on this intersection of those domain fields. But I think I'm in a very unique position to talk about this topic in the sense that I treat myself as a very in-depth practitioner of data science and developing mathematical, statistical, and computational tools to push the foundations of the data science, and also to contribute to new scientific discoveries. So over the past few years, including my time in grad school and also my time at Michigan, I've done a lot of projects and conducted a lot of collaborative work with domain scientists to obtain scientific discoveries. So in this talk, instead of talking mainly about general theme of data science, I would really try to use my own personal experiences with my practices in data science to actually talk about this topic of data science. And I hope that my own experience will be motivating for some of you here, either from the methodology side or from the domain side. And also I'll talk about the do's and don'ts in typical data science applications. So this particular graph that I'm showing here is what they call data science life cycles. So you can start from anywhere. For example, typically we'll start from here, capture. We have data acquisition, data entry, signal reception, data extraction. And this is called data pre-processing for us in statistics. And we do have many techniques for data exploration, data processing. So this is obtain the data, and then we need to put the data somewhere. So this is related to hard architecture. For example, at the University of Michigan, we have the Great Lakes system where we can store the data, and we can also have all of the computing resources. And we also have other system of data storage. For example, the Deep Blue by the library. And the next step is really the data processing. And this step involves more of the mathematics, statistics, and computer science, because this involves computational algorithms, mathematical models, and also visualization techniques. And then data analysis also in the domain of mathematics, statistics, and also some part of machine learning. We need to, for example, do prediction analysis in some of the cases. And finally, it's about visualization reporting. So that's about communicating the findings from the data analysis to domain scientists and trying to understand the outputs of the model and make scientific discoveries. And for example, in business setting, it's about decision making. And this actually goes to a loop because finally the analysis results might indicate something about data processing again. So we might actually start from scratch again to build a new set of models. So this is what they call data science life cycles. And this is actually what we do on a daily basis for a lot of the data that we analyze. And to me, when I first saw this, I feel, well, I'm only within this small domain. That means I'm in the mathematics and statistics little circle. And I don't know so much about the IT side. I don't know so much about the domain knowledge. Then how could I practice data science? And I know for a lot of the scientists that I work with, they would in our first conversation, they would tell me, well, I have a really interesting scientific problem, but I actually don't know the jargons that you guys use. I don't really know how to describe it in a mathematical model for you to work on. And I don't know what kind of computational or data architecture that I need to solve my problem. So, so the question goes to what is necessary to play with data science if each researcher only claims expertise in only one of those domains? So that comes to the story of collaboration. So I think for data science practice, especially for scientific discoveries, very close collaboration among statisticians, mathematicians, computer scientists, and the domain experts actually is quite necessary And it's actually, if the collaboration turns out successful, it's actually super efficient to obtain data-driven discoveries. So in this talk, I will focus on this aspect. So there are a lot of buzzwords that will make one sound like a data scientist. So even if I don't understand so much about any of those aspects of data scientists, I can still use those buzzwords to trick you in the sense that you feel I'm a data scientist. And these kind of buzzwords include high performance computing, AWS, cloud computing, for example, Google Cloud, PyTorch, TensorFlow, computing resources, random forest, support vector machine, principal component analysis, and then neural network-based methods, convolutional neural network, GANs, and LSTM, the long-term memory neural network. So these are some big buzzwords that for statisticians, maybe this line is the most familiar. They actually know how to derive the theory of all of these. And then for machine learning people, they are very good at different kinds of architectures of neural network. And this is kind of like a necessity for almost everyone because it's the essential coding language. And for high performance computing, people will know more of that. However, given those buzzwords, what are the good practices of data science? So typically, I think for good practice of data science, many ingredients are actually necessary. Domain expertise is the top priority, in my opinion, because data science driven discoveries needs to be based on domain expertise. And without that, it's actually useless data analysis, in my opinion. And then mathematical and statistics, how to transform the scientific question into a mathematical problem and write the equations down to solve the problem. Algorithms, optimization type of algorithms are typically useful in different kinds of context. And in some cases, we also need to make inference, for example, coming up with uncertainty intervals, p-values, prediction intervals. Computational architecture, sometimes, for example, for neural network fitting, we need to use GPU computing supplementary to CPU computing. So this kind of architecture needs to be managed. And also sometimes we need to have parallel computing because of the size of the data and because of the computational efficiency concerns that we have. So parallel computing and how to allocate the different nodes and how to use high performance computing in this case. It's actually another very important aspect that we deal with on a daily basis. Data management, this is something that don't really occur, for example, in statistics courses that we teach. However, in collaborative work, especially in the field of environmental science, there are a lot of imaging and video data. So the data volume can range from several gigabytes to several hundreds of terabytes. So how to manage the data and how to extract them for different kinds of uses is another big thing that we talk about. And also in the machine learning field, recently people have been talking about machine learning ethics and fairness in different kinds of methods, which may or may not apply to the environmental science settings. But in general, to have a good practice of data science, all of these aspects needs to be taken good care of, in my opinion. And in most of the cases, in my collaborative work with people from space sciences, the ones highlighted, domain expertise, mathematical statistic models, computational algorithm, architecture, and data management are actually all very important aspects that we deal with. So I just want to introduce data science practice from a very kind of like life experience of home buying. So recently I have been going through this home buying process, and I find the game really interesting. And actually I can find a similarity between home buying process and data science practice. And I know majority of people here know the home buying process, so this might be a very gentle introduction to the data science practice. So in my view, the buying agent and the seller are actually the data scientist, and they want to satisfy the needs of the buyer's family which are the domain scientists. So the key steps involve, first, the buyer's family needs to identify what you need. Do you need a big backyard, or do you need a really high ceiling, and other type of things? So parallel in data science practice, the domain scientists actually need to clearly define a scientific problem. It's not really like, I have this data set, I don't know how to use it, you help me to do something with it. That's not the good data science practice. Domain scientists typically come up with a pushing issue. For example, I have incomplete data, with some sparse observations, and a really high dimensional vector of predictors. How can I make efficient predictions for my model? So that's the kind of thing that the domain scientist will try to come up with, or try to communicate with the data scientist on it. It may be in a language that's not exactly what I was describing as a data scientist, but it should be something like that. And then the next step is really for the data scientist to search for different kinds of model and then do trial and error. So this is really the process of the buying agent trying to find the different homes that might satisfy your need, and then try to showcase the home to you every time. And then finally, they want to communicate on mutual benefit. So for the home buying process, it's essentially the buying agent is earning some money from it, and then the buyer family try to locate a home. And then in data science practice, it's really that the data scientist is trying to build up a model or come up with a data science methodology that will work for the domain problem using that particular data set. And this needs very close collaboration. Think about how many phone calls the buyer's family have with the buying agent. And that's the number of Zoom meetings or in-person meetings that a domain scientist needs to have with a data scientist in order to make progress. And finally, for home buying, you finalize the deal. And then for data scientists and domain scientists, typically a software package or a research paper is the final product. And in delivery of that product, it's really that the data scientist needs to clearly communicate through either numbers, summary statistics, or visualizations or tables to convince the domain scientist what are the key findings. And then it is the domain scientist and the data scientist responsibility to translate those numbers and the figures into scientific words, into scientific discoveries. And then they need to provide evidence for all of these scientific discoveries. And things like sensitivity analysis and also robustness of the results will also be tested. So that will finally close the deal in this practice. So in my view, for a complete data analysis, we need to be aware of the following key aspects. First is what we call data or sample collection aware. So this is typically ignored in many of the data analysis because people will just say, I have a data set that might be for prediction model. I'll just use a random forest to do my prediction or do my classification. However, how the data are collected, whether the samples are collected in an independent fashion, and whether there's any bias of the sample collection problem is actually very important because the result will be highly dependent on the samples that you collect in this case. And we have the words garbage in, garbage out. So if you try to guarantee that the sample collection process is actually principled, then the result of the statistical analysis or the data science model will actually be something that's valid. Otherwise, it's not the case. So this is something that I do want to bring people's attention on. And the second aspect is domain expertise incorporated. I see this point as being important in the sense that I see a lot of the practices of like statistical models, especially in some type of data science competitions. Actually, people just have a particular data set where they know which are the predictors and which are the outcomes, and then try to train some kind of model, for example, gradient boosting machine or random forest or neural network to get a good result. However, without domain expertise, actually sometimes the models cannot really perform to its full capacity. And in our experiences, the domain expertise actually can come up with, for example, good features in the feature engineering step, and also come up with good sample selection and good interpretation in the data science process. So this is quite important. And the third one is called principled data analytic methods. So there are so many tutorials online about different kinds of code that you can directly apply to your data to come up with some kind of prediction model or come up with some type of p-values that you might be using. However, we do need to be very careful about this kind of methods or blindly using those code, because as a statistician, we work with different assumptions and different modeling approaches and computational algorithms all the time. We are highly aware of the potential pitfalls in different kinds of blindly applying different methods. And I will give concrete examples in the tutorial once we come into the detailed mathematical models. So in here, I just want to mention, although there are many software packages that's available out there, sometimes we need to examine the underlying assumptions of each model that we're using and see whether that applies to our data and to see whether that's an appropriate analytic method. Otherwise, the analysis will be invalid and it's not trustworthy. And I think in this workshop and the tutorial, I think one of the objectives is to equip you with the tools that will be useful to perform principled data analytic methods. And that is the reason why I think Jonathan was mentioning some knowledge in calculus and linear algebra are actually useful. And the fourth aspect that I want to mention is we want to have informative visualization and summary statistics for a lot of the analysis. And advanced visualization tools are actually very important to deliver scientific discoveries. And we'll also introduce some of that in the tutorials when we come to the details. And finally, we need to give novel scientific insight and discovery based on the data analysis results. So this is what I call the key aspects from a complete data analysis task. So in terms of the tutorial on teaching the fundamentals of data science, I'm trying to borrow the syllabus of the curriculum offered by the data science curriculum at Berkeley. So they have two sequences of the courses, and I'll try to cover some aspects of the different topics that's covered in that particular data science course. So there are foundation courses, for example, programming. This is also emphasized a lot in Jonathan's talk, and we're in strong agreement that programming is actually like a communicating language in the future that almost everyone needs to be able to do something on it. So this is a very low bar to practice data science, even if you collaborate, even if a domain scientist collaborate with a data scientist, basic programming is actually needed, because sometimes to deliver the scientific discoveries, sometimes the visualization needs to be done by domain scientists to actually give the most efficient visualization. And the other is research design and application for data analysis. This is related to what I was talking about, to be data or sample collection aware. You need to, sometimes data scientists or statistics expertise needs to be incorporated into the initial stage of research design and also the sample selection. And third is statistics for data science. That's my expertise. I will cover a lot of those. Fundamentals of data engineering, we need a lot of that too. Applied machine learning, these are the basic. And the more advanced courses, and these are also more important aspects. And I think if these kind of tools can be incorporated into grant writing, it actually will make the grant seem stronger. First is experimental design and causal inference. Those are related topics and very important nowadays. And causal discovery is actually one of the trends for scientific discovery. A very simple example is whether smoking is causing cancer. So there's a strong correlation between people who smoke and people who got lung cancer, but is it a causal relationship or not? So there's a formal theory of causal inference that studies this type of problems. And the second is behind the data, humans and values. And this is something that's not my expertise, although I know this is quite important and it's related to what I talk about, the ethics and the fairness behind machine learning. Deep learning in the cloud and at the edge. So deep learning is actually something that's quite interesting these days, being applied to various domains. And an advantage of the deep learning is that it can capture the nonlinear relationship between your predictors and your outcomes in many of the settings. And it's a very highly flexible set of models. And the common critiques of some of the deep learning models is that, first of all, it's lack of interpretability, and second of all, it cannot come up with a uncertainty quantification for those. And in the recent research I see in the deep learning world or in the machine learning world, people are trying to come up with interpretations based on post hoc analysis of deep learning models, for example. And also people are trying to come up with prediction intervals, for example, coming from deep learning models. So those are actually new tools that I think those aspects should be added to a deep learning model when we analyze scientific data. And then statistical methods for discrete response, time series, and panel data. I think this might be the most relevant for the environmental science field because time series type of data and panel type of data, that means the a panel of the time series, and also spatial type of data actually quite important in the environmental science field based on the data type. Machine learning at scale. So scalable computational algorithms and efficient computation, including MPI, the parallel computing resources actually becoming more and more important nowadays with machine learning practices. And I think this actually should be emphasized quite a bit in daily practices. I don't know if we have the time to cover that in the workshop. Natural language processing with deep learning, this might not be the most relevant in our setting. Data visualization, I would say this is super important. And this should be developed based on each domain with a unique features. And machine learning system engineering, this is not something that I'm an expert on. Computer vision, and this is also something that's quite popular and quite powerful. And we'll hear a talk on this in a few minutes, I think. So here, with my last 10 minutes, I just want to talk briefly about some relevant jargons and techniques that talks a lot, in my opinion, in the field of environmental sciences. The first one is regression, second is feature engineering and selection, dimension reduction, time series spatial temporal model, and experimental design and neural network. I think as compared to the course syllabus that I just mentioned, this is actually a much smaller subset, but I think those are essential things that people should be aware of in terms of data science practices. So I'll just give a very gentle introduction to two of the topics and leave the details and the implementations and also more discussions to the tutorials that we have. So regression models essentially examine the relationship. It could be a linear or it could be nonlinear relationship between a predictor that's called X and a response that's called Y. So in some field, they call it independent variable and dependent variable, whichever way you want to call it. Typically, we call it parametric model because it's parameterized by a particular unknown parameter beta, and this beta is going to be estimated based on real data. And in real data analysis, we typically have a noise term. That means the data is not perfect. There is some observational noise related in this particular model. So essentially, this F describes the true relationship between the predictor and the response is indexed by some unknown parameter beta. And then there's some observational noise that transform the true process to the observations. So in this simple linear regression model, or we call it list of squares, it's actually a very simple relationship that the X times beta is equal to Y. So the fitting of this model is actually very simple. It could be done in the software. And typically we use this type of models for predict what happens in the future, and for interpolation for the points where we don't observe, we don't have an observation, what is the response? And also we want to interpret, for example, is it a positive relationship or a negative relationship, or is it a nonlinear relationship? So that's about the interpretation. The regression models that we are aware of that's quite popular include the linear regression models, which is very simple, but people have been using things like lasso, the sparse regression models in practice. Generalized linear models that can deal with all kinds of responses, for example, categorical or ordinal type of response. Random forest, this is too popular for me to introduce. I think almost everyone have heard of this. However, in daily data science practices, for example, in the problems where extrapolation for a prediction model is really important, random forest may not be a good choice in practice. So it has turned out to be good prediction models in many studies, but in practice, we need to know the underlying assumptions of the random forest and the underlying architecture of the random forest in order to see whether it's the most suitable models for our task or not. And another very important aspect in data science practices that I work with, and also that I see my collaborators are struggling with, are really feature selection and engineering. So essentially in this feature selection and engineering process, we try to remove non-informative or redundant predictors, sometimes through transformations and sometimes just by screening. And also feature engineering is also another very important aspect. For example, for some of my work, we have imaging type of data. However, how to extract efficient features from this type of images will actually be important problems. So for simple problems where we have vector observations, correlation analysis could give us a feature selection result. We need some kind of screening technique by studying the correlation between the predictor and the response. That means the correlation between the independent and dependent variables. Sometimes post-model fitting, we can obtain feature importance, and that actually also gives you ideas about the selected feature or what feature is actually contributing to the model more. And we have sparsity methods like the lasso that people have been using a lot in different fields, and this also enables feature selection. So essentially it's using a subset of the predictors to come up with a prediction model. And also we have robust methods. For some of the methods, it's actually quite robust to feature redundancy and also to the correlation among the different features. So sometimes we just directly adopt those kind of robust methods, although computationally it could be more challenging to obtain a prediction model. So that's pretty much what I want to cover for today. And I will leave a lot of the details, including the coding techniques and the visualization and the principles to statistical models to the tutorials. And feel free to email me or let me know if you have any suggestions on the concrete topics to be covered in the tutorials.
Wonderful. Thank you so much, John. At this point, we're going to start our round of talks from various faculty who work in this domain. So I think our first speaker will be David Fowey. David, are you here? Yes, I see you.
Yes, I'm here. Let me just pull up, make sure I can do, I just have to do, let's see. I just want to be able to see also like the chat and stuff. I can start if you'd like.
Yes, please do.
All right. So I do computer vision, and I wanted to talk about two collaborations I've done over the past few years. One of which was sponsored by MIDAS on measuring sort of big things and little things. So I do computer vision. My normal work is in measuring sort of normal households type stuff in 3D, and I've been very excited to take some of these techniques and apply them to other things. I'm going to talk about the solar magnetic field, as well as bird skeletons. And this is joint work with dozens and dozens of people, as many collaborations are. So let me just talk briefly by motivating why I sort of got interested in this work. And so here we have a picture of the sun. It's viewed in ultraviolet wavelength, and so it's really active and doing lots of interesting stuff. And over here, just to give you a sense of scale, at the bottom left is actually Venus. And one of the things that's exciting about the sun is it drives a large amount of just stuff in the world. So that, this is the source of all the energy that we have, ultimately, and it's also one of the sources of a lot of sort of really actually dangerous things and stuff like, for example, extreme space weather. And it's also like you also get these beautiful pictures, which is a lot of fun. And one of the things that is the case, in addition to producing beautiful pictures, is it's one of the sort of large sources of potential danger for basically for the nation in general. And actually, extreme solar weather is one of FEMA's there are two national level threats recognized by FEMA to the United States, one of which is pandemic, and the other one is extreme space weather. And these are sort of two things that FEMA is really worried about at a national level. And so naturally, if people are worried about this, there's lots of great instruments for monitoring the sun. And one of the things that's been very exciting for me, I work on really data-driven stuff, is that there are loads of instruments. And so if you have the magnetic field and you sort of unwrap the magnetic field all the way around the sun, there are instruments observing at all sorts of different vantage points with different resolutions and abilities. And so there are instruments that measure the entire field of view from a perspective. Instruments that measure little tiny pieces. There are instruments on the other side of the sun, and there are instruments that are now flying towards the sun, trying to collect great data. So there's all this wonderful data. And as a practical thing, one of the things that you can do to, as someone as a domain expert who has problems for people to solve, one of the things you can do to lure people like me in is you say, hey, I've got all this great data. And often people are saying, oh, cool, data, and then I can do something and be useful. And so one of the reasons why I got lured into working on the solar data is that people said, hey, we've got tons of data for you. So let me talk a little bit about some of this data. Here's one of the satellites that I use for our work. And it's the Solar Dynamics Observatory, and it produces basically enormous 4096 by 4096 images. So this is like a HD image. And it comes with calibrated measurements, which is really amazing. And there's tons of details that go into this. And it produces stuff in real physical units, which is very exciting. So if you make some predictions from a model, you can actually translate this into sort of real life, which is pretty exciting for me. And it's also one of the things that is exciting as a domain expert that you can provide for other people is you say, hey, I understand the process. And so one of the things that drew me into working with astrophysics people is they have models of how stuff works, and they're approximate. They don't always work, but they have a good understanding, and they can explain to me lots of things about how their data works. And as a machine learning person, I don't understand how plasma physics works. But if you say, hey, I can explain to you this process and this model, this phenomena, it's very enticing actually as a machine learning researcher to find a domain in which there are very well explained behaviors and things. And so let me talk briefly about how one of the things we've been able to do with this data, which is basically producing synthetic versions of estimates of the magnetic field of the sun. And along the way, I'm going to tell you some collaboration lessons I learned, which I didn't know coming in, which might be helpful for you, for stuff you might want to start. So one of the things the thing that underlies everything that the sun does, many of the things that the sun does, I can hear my collaborators shouting at me, is that there's a strong magnetic field, and this magnetic field drives a lot of the effects that you see. And the way that you actually observe the magnetic field is that when light passes through the magnetic field, it changes how light appears. Essentially, there's something called the Zeeman effect, and people have worked out, essentially, given magnetic fields, what sorts of light should you see? And so if you want to get at like what's the magnetic field of the sun to understand like active regions, solar flares, coronal mass ejections, all sorts of nasty stuff, you need to be able to actually measure this magnetic field. And the way people do it is you take pictures of polarized light and you try to figure out what magnetic field produced it. And the standard way people do is you have an optimization procedure. This is called an inversion algorithm that takes the observations and turns them into a magnetic field. So basically, you can think of this as a big guess and check program where you guess what the magnetic field is. You say, that doesn't look like the light we see. You just guess another one. That doesn't look like it. You guess another one. Okay, that's looking better. And the goal is you can find a field that explains each pixel in the image pretty well. And these produce things like the strength of the field, the inclination of the field, the azimuth, all sorts of other properties. And there's an existing system which works quite well. And something called the very fast inversion of the Stokes vector. And this is something which runs inside a NASA pipeline, and it produces the outputs. And there are lots of papers to explain what it does. And it works pretty well because people have been using this for over a decade. The catch is it takes about 30 minutes an image, and there are lots of weird oscillations. So if you actually use the data from this, you find that the sun oscillates. Its magnetic field oscillates at around 24 hours frequency, which is basically not possible. So there are all sorts of really nasty bugs. And one of the things I learned along the way is that actually, as your collaborators explain to you all the issues with the data, sometimes there are interesting fixes that the machine learning expert might be able to help with. And so it's actually quite, you should not, like, your data has nuances and tricks and catches. It's great to explain it because you might find interesting solutions. There are also all sorts of biases, and actually fixing all these biases is basically impossible because it takes 30 minutes a disk or sort of a picture of the sun to actually produce stuff. So one of the things that we did is actually one of my collaborators during a meeting, he just texted me and said, I have a really silly idea. Why don't we just make a deep network that pretends to do this pipeline? So there's this pipeline that takes 30 minutes an image. Let's just emulate the entire thing. And we just made a pipeline, a machine learning system that emulated the pipeline. And it basically emulates everything, all the good parts, all the bad parts. The only thing that it can do is it can do this much, much, much faster. And just to give you a flavor of how this works, what happens is we have the observations that the normal pipeline uses, and we have a deep network. And so this is a convolutional neural network. This is what I do most of my time. And it produces an output. And you try to get the output to match what the pipeline produces, what the physics model will produce. And you try to basically compare the output of this function with what the pipeline says, and you try to make sure that these are as close as possible. And in some sense, this is actually not from the machine learning perspective, there are loads of details to get right, but it's not a super exciting or innovative technique, which is fine. Because what ends up happening is we can essentially at full resolution produce results in about 5 seconds compared to about 30 minutes. And this is before we do any sort of optimization whatsoever. And what ends up happening is this ends up being a pretty effective tool for producing information about the sun way faster, because instead of taking 30 minutes an image, we now take 5 seconds. And this all of a sudden unlocks lots of other things. Like if you wanted to correct artifacts, if previously it was going to take 4 weeks to get the results, now it's going to take more like a day. And so you can dramatically accelerate lots of different subsequent processes. And one of the lessons that I learned was that sometimes you got to pick the right problem rather than doing the cool problems. And so these are two of my collaborators, and they basically pitched to me these problems that are actually really simple. And actually, in some sense, starting off doing this simple problem the right way, where you get both the domain right and you get the machine learning right and the statistics, and you make sure everything is really exactly perfect. That's really hard, and that's hard enough. And so you want to start with something really simple as opposed to doing something really cool. And figuring out what the right problem is can take a lot of time, and you need this bi-directional trust between you and your collaborators. And this took a while, and then eventually we realized we were talking the same language, and hey, here's an interesting problem that I think I can solve that is actually of use. So here's some output. So this is what the physics model produces. And here is what we produce. You can flip back and forth, and over Zoom, the images are so compressed that you can't see the difference. Now let me just sort of zoom in. And one of the things that if you have a great eye for color, you'll notice that yellow spots are going to be basically where the magnetic field is stronger, and our yellow spots are slightly less bright. But overall, if I sort of took this image and shuffled them around, what we found is that it's actually very difficult to figure out which is the result that's produced by the model and which is the result that's produced by us, which is pretty neat. And I promise we do metrics beyond this. We don't just look at the pictures and say it's good enough. And in fact, metrics are very challenging. This is the inclination of the angle, basically the angle the magnetic field is pointing, and we produce results that are actually quite similar. It's potentially not going to come across over Zoom, but there are little dots actually in the outputs from the pipeline that actually our model kind of smooths out. And so these might be sort of bad pixels, and our results will smooth those out, which is kind of nice. One of the things that we discovered is if you take the if you take this pipeline and you look at the lots of different measurements, like the one of which is basically on average what direction is the magnetic field facing. And if you look at this over time, if you look at one day, you get some sort of plot, and this kind of looks like cat ears, my student says. And so we can say, like, what happens? Do we get cat ears the next day? And the x-axis is the hours, and so it goes from 0 to 48. And what happens is you get the same motif, and from day 1 to day 2. And this is just this, at every single time we look at the average angle over the disk. And what happens is if you plot this over a very long period of time, you end up having this sort of oscillation that I talked about before. And one of the things that we discovered is that actually if we take our deep network and we produce the output, we didn't ask it to have an output that you could kind of sum over the entire disk. It actually reproduces this artifact really nicely. And to some extent, that's kind of bad because we've reproduced the artifact. But on the other hand, it means we've perfectly emulated, or not perfectly, but very nicely emulated the pipeline that people currently use. And so if you want to fix this pipeline, you can use our system, which is orders of magnitude faster, hundreds of times faster. And so this suggests that we can actually sort of maybe use the deep network as a proxy for fixing the issues in the pipeline. One of the things that I want to mention is that the stuff is that metrics kind of need close collaboration. I wanted to just use pixels, and my collaborator said, let's actually look to see whether you can reproduce these artifacts. And so I would never have thought of these ideas. And so it's really great to have bidirectional communication where you say, hey, will your system be able to do this for me? Because you know what questions need answering. The collaborator you have doesn't necessarily know that. And so having this bidirectional communication is really important. Let me just skip the impact. And one of the things we're also producing is producing sort of synthetic instruments that can combine two instruments and produce best of both worlds stuff. But I want to leave you with one sort of collaboration bit of advice that I learned from Tomasz Gambosi, who helps run an entire center, which both Yang and I are involved with, which is one of the things that Tomasz taught me is that if you can speak the same language early on, this is really important because we were able to communicate, my collaborators and I, by knowing a lot of the same language. They knew linear algebra and data, and I knew a little bit about solar physics. And we worked really hard to collaborate. So I asked lots of really silly questions, and I got lots of really good explanations. And someone would sit me down and explain to me how stuff works. And this is really important because you need to build this trust and you need to be able to speak the same language in order to pick up on the right problems. So I'll conclude by showing you one last really neat thing, which is, I think, another problem we've worked on. So Brian Weeks at the School of Environmental and Sustainability emailed me about bird skeletons. He said, I want to measure lots and lots of little tiny birds. I thought this is great. And bird size ends up being correlated with temperature. And so you can study climate change, morphology, lots of good stuff. And Brian, this is part of his pitch. He said, hey, look, we can study all this sort of stuff. Now, bird skeletons there are lots of them. And the University of Michigan has like 25,000 of them. But you can't measure them because it takes forever, because these birds are really tiny, and measuring really tiny stuff takes a really long time. And so we built this system that kind of looks at pictures of bones like this. And the problems are the bones all look the same, but all the bones look different between the different species. That's the entire point. And the bones will overlap. So if you dump the bones in to like onto a table, like they all overlap. And so we built this system. Brian built this amazing box. We called it Skeletor, and then we realized that there's some copyright issues. So now it's called Skelevision. And you can see the little Skeletor sticker on the left. And basically there's an expensive camera, like a really nice camera, and there's a mechanical system that can dump bones and sort of put them back into the little shoe boxes that they occupy. And along with a student, we built a system that is basic computer vision. It basically detects the bones in 2D, and you can measure them by pretending they're on a plane. And the vision system is really, really simple in the sense that we just apply the right system, we do it the right way, we get all the little details right. And these are really hard. And I had a student who's like an NSF fellow now at a prestigious master's program, and he spent a lot of time getting this to work really well. And it took a lot of effort. But the system itself is actually, in the end, really simple. And you just have a standard off-the-shelf system that I teach in my undergrad computer vision class. But you do it the right way, you can actually get good results. And what we found is you can reduce the capture time by like 15x. And the accuracy is about as good as a human, and it's actually very repeatable. And so you can build the system, and all it does is detects bones, and you can measure them pretty easily. And the thing that I learned from this is that one of the things that's useful, and as you're looking for collaborators, machine learning people are experts in areas that aren't their main focus of research. So I don't do object detection, but I know how to apply object detection systems because that's my big area. And it took a really long time to get this. And from start to finish, this was a very long project because there are lots of bones involved, but the payoff can be really worth it. So in the interest of time and maybe taking some questions, that's it in terms of some of the stuff we've done and some of the lessons I've learned. But the long story short is it's very important to have collaboration and communication, and it has to be bidirectional. You can pick the metrics, the insights, and the data, and it's really important to have this trust between the collaborators in order to have really great results. And so in the interest of time, and I know that if you have back-to-back professors, everything will go over, so I'm just going to shut up from here. But I'm happy to take questions.
That's excellent, David. Any questions for him about this talk? This is a great talk.
I have a question.
Yes, please.
So where do you get all these solar data? Are they available online or?
Yeah, these are all available. So NASA has had a long track record of trying to get all the data publicly available, which has been very, very useful. And one of the things that I found actually very helpful has been if you can get the data into your collaborators' hands and have it be as publicly available and as easy to access and get them all the raw data, this can be very helpful. So NASA, there are sort of services for requesting the data. And in follow-up work, I've even ended up, you need to get the machine learning or computer vision expert, you want to get them access to the raw data so they can go pouring through, and like, we've been doing stuff like trying to figure out, are the telescopes pointing information? Is some of them are actually inaccurate? And I'm pouring through headers of files trying to find out what temperature things are, because these are correlated with actually the telescope bending. And so having access to the data is really important. And although of course, there are certain types of data where you can't just like dump that data to the internet. You can't just dump all of Michigan medicine to the internet and say, hey, here's a data set.
Any other questions for David?
And yeah, I have a related question. So is the algorithm that you apply to these data, are they like scalable to really large data sets, or is the processing time linear or exponential based on the amount of data you have?
That's a great question. It's really tricky to quantify the processing time for fitting any of these models, because in some sense, if you get more data, it doesn't necessarily improve the model in a linear way. It's often improving it in like a logarithmic way. So one, processing time is a huge issue. But the way I'd say it is that throughout my entire career, the amount of time that algorithms have taken to train is about a week. And that just simply is human patience. And so the models get deeper, the GPUs get bigger, and it's always about a week, because after a week, people say, can't take it anymore. But typically a lot of these models, like for example, in the bird skeleton case, the amount of data we have, and so my student, Brian, me, like everybody was in like labeling bird bones, and they gave us the easy bones, like humerus's are really easy. And so we were in labeling data, and so that was the limit for us. But for the sun, there's just it's like 10 years of data. At every 12 minutes, you get a new observation, and it's a flood of data. So, but the catch is that data doesn't improve your performance like linearly. It's just very, very quickly saturates. But they're generally pretty. Yeah, it's generally most algorithms, if you can imagine, that you can train a good version. You can't necessarily train the best version, but you can train a very good version pretty quickly.
Excellent. Well, thank you, David. I think it's time for Zach's talk. So again, thank you. And Zach, please share your screen when you're ready and begin.
Yeah. I think David needs to unshare, right?
Yes.
I have unshared, yes.
Thank you, David.
Okay, so you see the screen?
Yes, I can.
Okay, good. So yeah, so today I'm going to talk to a new type of data actually we have in seismology, and that's David will understand why I asked this question actually. So which is using fiber optic cables to do seismology or geophysics in general. So I made this slide recently, like what is a seismologist? So seismologists, we do study seismic waves for a living, and it's a combination of many different things. First of all, seismology is an observational science. So we do take the time sometimes really to look at the seismogram and discuss, like in the seismocoffee or something like that, we take a seismogram and we try to get some information about the Earth interior, thanks to the different phases and the waves that we see on the seismogram. So that's what my mother think I do. And at the end, there is also the end member would be what I think I do, which is really data science, because we are like overwhelmed with seismograms. No, we have seismogram from everywhere. We have continuous flows of seismogram that you can download online or that we are currently recording elsewhere. And yeah, the last image, what I really do, and I think I can put that in parallel with the chart that Yang Cheng showed earlier, is because our science, data science, is actually a mix of so many different fields of science that it's very hard to be very sharp and to define yourself as a complete data scientist. And as David said just earlier, it's very important to have collaboration, to have like people working in each of these areas in order to have finished research on what you are doing. And so next. So what we do, why do we study earthquakes? So the first thing we can do, obviously studying earthquakes, is like locating the earthquake, having an information about the source of the earthquake, how big was the rupture, how big was the fault, and so how big was the earthquake. And then the wave, they travel at different velocities, they travel through different materials, and so you can retrieve some properties of the Earth interior. But seismology is a more complete science than just looking at seismic waves. In fact, we also look at GPS data, so displacement, at satellite data, ground deformation, at the geological structure, at the fault system, at the different stress that are transferred, at the very local seismic structure near the seismometers, and even through paleoseismology to know what happened in the past, to give more information today. And so the very end member of this would be like to have an integrated hazard prediction model. So here you have an example of a rupture, a fault that sleep in the Salton Trough here in Southern California, and you see what you see here actually are the waves propagating through this model, but this model is like kind of integrating all the different observable that I just discussed. And so now we can have a better idea in case an earthquake of such magnitude would occur in this region, how would be the shaking in the Los Angeles basin, for example, where obviously the risk is very high because it's one of the largest cities in North America. And based on all the observation we have, not only seismologic, but also geologic, we observe that, for example, in the case of a large earthquake, you see that the waves, they're actually trapped here in the Los Angeles basin. So the wave front here is still, it's like moving away, but even several seconds, tenths of seconds after the wave front passed, we still have very strong shaking in the Los Angeles basin, which of course pose a significant risk for the population. And so that's just an integrated study that would take all these parameters into account. And that's really like the end goal of what we are doing. And to observe waves, we have different types of seismometers. They have different properties. They can record wave over different frequency bands. They can record wave at the ocean, the bottom of the ocean. Some are very expensive, some are very cheap, such as the Raspberry Check is only like, I think, less than $100, and that's an accelerometer. So it's very sensitive to certain high frequency and not the low frequency. So when you design a seismic array, you need to take all these parameters into account, price and sensitivity, based on what you want to analyze. And one of the first seismic array that was developed in the early 80s was actually developed to monitor nuclear explosions worldwide. And here, all the stars that you see are the global network of seismic stations. And when an earthquake occurs, you can pick the different phase of these earthquakes. And so you get an idea of the velocity of these waves at different, measured at different location. And so you can have a rough idea of what are the properties of the Earth, the global properties of the Earth. Then we had in the early 2005 to 2015, more or less, we had this kind of gigantic experiment for us seismologists, which was the US array, which was spanning seismic station, high quality seismic station all over the US. And so in that case, you can directly observe the wave field, the seismic wave field traveling through the continental US. So that gives you more precise information at a much smaller scale. And here it's another example of the price of the seismometers getting even lower, a few hundreds of bucks for what we call these nodes. There were in the also 2015 around this date, some very dense array measurements. So here the stations are spaced by less than a few hundreds of meters. And so this is the Long Beach area in Los Angeles. And here it's an earthquake that's traveled through this array of more than 5,000 stations. And so seismologists use these images to infer properties of the ground motion and of the interior of the Earth. And what we are doing in my group, it's kind of a new type of seismology, which is using fiber optic cables to measure ground motion, so the shaking of the ground. So we use what is called a distributed acoustic sensing, which basically throw a pulse of light, a laser at very high frequency in a fiber optic cable. And so here it's a fiber optic cable in Spain that is used normally for telecommunication, for internet, between between Valencia and Palma, so between the main peninsula and this island in the Mediterranean. And so when the light travels through the fiber, so part of the light is actually backscattered, as you can see here in this example. You have a laser in a PVC tube in this example, but the working principle is the same. So you have some of the light which is backscattered, and because we know the speed of the light in these fiber optic cables, we can interrogate how the backscattered light come back to the interrogator. And if there is a change of phase in the backscattered light, we analyze this change of phase in continuous time, and we interrogate at many different places or over the fiber. And so we have like something which is like a seismogram, which give you like it's a time series, except that instead of measuring velocity, which are what generally measures most of the seismometers, we measure the strain over the fiber. But in that case, you see that in this example, we measure the first 50 kilometers of the cable, and we transform that into an array of 6,000 seismic stations. No, they're all spaced by a few meters, and you have on the background in black the national seismic network in this map, where you have 4 stations that recorded an earthquake, and here we have more than 6,000 stations. So you see, we have like 3 orders of magnitude more data than the national seismological array here in this example. So we have much more data using this. And so this is an example of an earthquake wave field that you can observe using this type of data. But the question is, why do you want always more data? Or why do you want always going more granular? Well, it's for us, this is like the mathematic part of the equation, let's say, of the chart we showed earlier. Well, if we want to solve the wave equation, there is actually a spatial component into this wave equation. So it's important, if we want to understand very well our model that use this wave equation, we also need to have and to observe the data that kind of fit this model better at a much smaller scale. And so we can actually now integrate better the spatial component. And here is a map of the commercial fiber cables around the globe. And these are only commercial. For example, University of Michigan has its own fiber network to communicate between the different building, but also supercomputing centers in the North Campus, Central Campus. So they own their own fiber. And what I mean is that there are much more, there are hundreds of thousands, even millions of kilometers of fiber that are already laid down in cities or in the ocean. And so if we seismologists could use only a fraction of this fiber optic cable, well, we could get much more information about the Earth interior and the earthquake processes. And so here it's just, I could spend a few minutes on this slide, but the only thing I want to talk here, so here are the pros and cons of this method, but I really want to insist on storage, because for us, it's really an issue. And just to give you an idea, what David mentioned about NESA, so they have all the data available. We used to have that as well in seismology. And this is the Incorporate Research Institute for Seismology, or IRIS, where basically when you write a grant and you say, I want to get some data, let's say in Colombia, because I'm interested in this region, then you have to publish the data on the IRIS website 2 years after the beginning of the funding. And you can see that in the last 20 years, so the amount of data is taking like it's really growing exponentially. And so right now, as March of 22, they have about 800 terabytes of data available. So these are almost all the data, let's say, publicly funded that you could download and get access. And here with DAS on the right, so distributed acoustic sensing, only in 5 years and a very few experiments that have been led, so it's less than 10 experiments, we reach the same volume of data, 800 terabytes. So basically, we have arrived at the point where institutions like IRIS cannot host the new data. we are at the bottleneck, and that's a real hassle for our community, because the problem as well is that this type of instrument are kind of expensive. So it's only the property on, let's say, rich research groups that can afford to buy this instrument or rent these instruments. And so many research groups in the US or elsewhere in the world don't have access to this data, because on top of that, they are not available online. So here at University of Michigan, we are hosting one of the largest hub of this data. Right now we have about 500 terabytes of data. We are trying to host up to 10 different data sets that we are sharing with the international community. So everyone with an email address can basically download this data through Globus, and they are stored on a locker, which is provided by the Advanced Research Computing at University of Michigan. So that's still a temporary solution, no? Because we will not be able to host all the incoming data, but at least we are trying to provide some data to new research groups that are interested to deal with this type of data set, which are truly amazing for our community. And here now, I just want to finish on a few applications that my research group, we are working on. So I said I am a seismologist, but I recently realized that actually this type of data in the ocean, they record seismic wave from the bottom, but they also record all the waves that travel on top. So let's say on top, which are the oceans. No, so we have wave, incoming wave, gravity wave, the wave that people use to surf on top of it. We have wave, wind wave. There are internal gravity waves. There are many waves that I didn't know about, let's say, a few months ago, and now I'm really into like trying to decipher all this type of wave that we observe in this data. And so here, what you see, it's just a few. So again, here what you see on this plot, you have, let's say, one seismogram. Each line, horizontal line, would be a seismogram. So you have different channels, and then you have time. The red line is where is more or less where the fiber cable go from land to the sea. And so we see that just applying a simple filtering, a bandpass filter, we observe this wave, that kind of slow wave. They travel at about 20 meters per second. And when they get closer to the coast, they even get slower. And so these are actually what we call the gravity waves, so the wave at the surface of the ocean. And if you look at it at another time of the day, they get higher on the beach. And so now we can even like monitor how tides are evolving. We can monitor the wave coming through this cable and the tides. So which is kind of new type of observation for this. And if you look here, I was only showing a few hundreds of stations, but we have a lot more of stations. And so you see this wave, these gravity waves traveling from very far away from the shore and getting near to the shore. And so we are developing an algorithm to track both in time and space the velocity of these gravity waves. But imagine that normally what we do, so we have, let's say, webcams, we have satellites that go, they are not continuously monitoring, they just go time to time, and they also have a very specific track. So if it is off track, you cannot monitor the ocean. And also we have buoys, but buoys is just one position in the ocean near the shore. And actually what you see in black is the displacement of a buoy, but with this fiber cable, we can now measure how these waves change in velocities over 50 kilometers. So we really have like the full picture of how is the wave field at the surface of the ocean evolving. And so here on the right is just a zoom on the first channels that are unshown here. And here we see that the highest change in velocity of this wave fits almost perfectly the tide model that you see the black lines here. And other type of observation that we can do. So we realize that these change in frequency, in time in frequency, they are actually due to storms in the Pacific or elsewhere. So using different arrays, seismic station, and these distributed acoustics channels, we can use the information that we have in this spectrogram to kind of relocate the storms in the Pacific using very simple triangulation algorithm. One thing we are trying to develop as well is when you have tsunami, that of course generate a pressure change on your fiber, and we are trying to detect very subtle pressure change that could be related to tsunami. And hopefully, maybe in the future, we could use these fibers to as a new tool to early warning of tsunamis near the coast. And here, I think that would be something to collaborate with David, actually. So this is really like a vision science. So we have this data, but these are very sensitive instruments. So we want to record earthquake, but we see that we also have waves of all forms in the ocean. So we have a lot of different frequencies, a lot of different signal that are stacked to another, on top to another. So we are trying to denoising this data, or trying to extract different features from this data. And so we have like data both in time, let's say 4 months of data, and space, like 50 kilometers. So we have like image. So this is like 50 seconds of data over for 40,000 meters. And so we would like actually to develop this type of detection through vision computing and get a better sense of what we get into our data. We also have, I'm thinking now that we also have data in cities, and in Mexico cities, or in Barcelona, in Spain. And so there are a lot of different signals, such as footstep, cars, and we need but there are so many signals that we need to classify that. And of course, we cannot do that manually. It's just too much data. We're talking about hundreds of terabytes of data. So we need to develop all these.
Thank you. I'm gonna have to
okay.
adjust
Sorry,
here, so
but I'm done.
All right, thank you. So maybe interest of time, we will have a discussion at the end of the day. So hopefully maybe we can have a further discussion about some of your work then. So thank you so much. Christian, please take it away when you're ready.
Let me share my screen.
Yes, please do.
Put this in presentation mode. All right, are you seeing full screen?
Yes, I am.
Alrighty, okay. Yeah, I'm really excited about the workshop and the bootcamp. So I would like to also present, I guess, a teaser talk. Yeah, so a 15-minute walk through the topics in climate science, or a potential topic in climate science. And this work is mostly done here by my graduate student, Garrett Limon, that he's pictured here. And I gave it a title, can machine learning approaches replace, the physical processes in weather and climate models? So it's, a question. The answer is probably yes, but you can also judge it. And I'm a professor in climate and in the Department of Climate and Space Sciences and Engineering on North Campus here in the College of Engineering. All right, let's start with an overview and some maybe questions we can ask. So I guess a very generic question is, can machine learning methods emulate physical parameterizations, physical processes in climate and weather models? Or we call them atmospheric general simulation models. It's an acronym. And you can ask a few more detailed questions. For example, yeah, how well can a machine learning algorithm mimic a physical process in these models? For example, is it real? You know, what's a physical realism? So just to give you a flavor of this, yeah, can we avoid, for example, negative tracers or negative precipitation, which we know is unphysical. So this should not be hopefully coming up. This should not be coming up, hopefully, in our machine learning algorithms. Or is a dynamic range good? For example, are you capturing the extremes in, you know, the weather or climate phenomena with your machine learning approach? Or yeah, what's the computational cost efficiency? And do you have enough data even to train your machine learning algorithm? Yeah, so you will actually see the answers to the questions here. And that's also related to my last bullet point. The answers also on the performance issue, they depend on a lot of details, for example, a lot of details concerning the data selection, your resolution, the model grid spacing, for example, even the machine learning architecture, whether it's a random forest or maybe a neural network, and also many of those tunable parameters, they are called hyperparameters in the machine learning algorithm. For example, this is just a flavor of one hyperparameter tuning model. It's called Sherpa. This is publicly available. This comes from UC Irvine, but there are others. So there are also tools out there that help us as scientists to make decisions about our machine learning algorithms. And just to maybe put everybody on the same page, what I'm talking about here is a regression technique, and we make predictions. And it's supervised learning. Yeah, so you have heard a few of these keywords. This is where I am in my talk. And of course, I only have 15 minutes, and I will not answer all these questions in detail, but I give you some hint, how we might approach these questions. All right. Yeah, for those who are not climate scientists and have probably never seen a weather or climate model, just this one-page teaser, what it is. So the background is that, we have these models that are put on the surface of the sphere like this. And of course, you have a grid on top, and then there's a lot of, we have a lot of equations to solve on this grid. For example, the fluid dynamics equations. And these would be then computed here on this model grid. We also, of course, have a vertical component. So here you see a couple of vertical levels. And everything that's really computed here on this model grid, we call, the resolved fluid flow. We, of course, need numerical methods for that. That's actually not the topic of this talk. The topic of this talk is everything which is super small. For example, rain or rainfall you see here, or radiation or friction, turbulent motions, everything that's basically too small to fit into, or that it's too small to be represented on this model grid. So imagine this is maybe 100-kilometer grid spacing, or maybe 50-kilometer grid spacing, but clouds and radiation, this happens at millimeter scale. So you're not resolving this at all. And this is when we put into these models, we call it physical parameterizations. Basically, we are estimating the effects of rainfall and radiation, turbulent mixing, and basically use these effects to force the processes on the model grid. This is what we have, and these are estimates. Again, and this is my target. So I'm targeting machine learning approaches for these uncertain small scale motions, subgrid scale motions like rainfall, cloud formation, or turbulent motions. So this is really where you and this is even uncertain from a physical viewpoint. So we have a little bit of leeway maybe in machine learning to do that. All right. These forcing mechanisms from the physics, you can mimic them in equation form now. For example, here's a horizontal velocity, and there's a very simple way maybe to mimic friction. This is called Rayleigh friction. It's linear, actually, as you see, and also solar radiation we could probably mimic with really simple approximations here. For example, a temperature relaxation to a known profile like this one. And by no means, this is not full complexity climate modeling. We are using here a hierarchy, basically a model hierarchy of a simplified model to learn about the pros and cons of machine learning. Yeah, but this is a starting point. And here we even start with a dry setup in this configuration. And this is called dry head Zwaris. Maybe you see that acronym later. We can also be a little bit fancier and increase the complexity of our model. And you see that now on the next slide. So we can, for example, still keep the friction, but then in the moisture forcing or here in the temperature forcing, we do more. And this is now a moist version of a simplified climate model. We still have the solar radiation simplified, but let me highlight the other things. So we have condensation, rainfall. We have maybe in the lower boundary layer, we have diffusion, turbulent diffusion. We have surface interactions. And also you see these processes then impacting not just the moisture DQ field, but also temperature. In addition, the precipitation that you get on the ground is actually an integral in the vertical of condensation. So this becomes more complicated. Yeah, of course, real climate models are even more complicated like that. All right, but let me show you now a couple of these performance studies. All right, the method is a supervised machine learning method. So we have inputs from the model. We have also output. These are the temperature variations and moisture variations over time. And we want to train this black box here with the relationships between the input parameters like temperature and velocity and the output parameters, which are the forcings, the temperature variations. In general, the more data, the better. We tried random forests and neural networks as kind of the two techniques. This is built on techniques in Keras, TensorFlow, or scikit-learn. These are these packages, Python packages that we can grab. And also at times we use the Chopper optimization tool to inform our hyperparameter choices. I guess I can be quick. So maybe you have seen random forests. This is basically a decision tree algorithm. And a neural network is kind of this, these connected nodes. I don't really have time to dive into any of this. And the bootcamp will also give you way more information, but just keep in mind, these are very different machine learning algorithms. All right. Okay, before I show you the results, I show you some ideas how to even generate the data. We are using a model from the National Center for Atmospheric Research, which is called the Community Atmosphere Model. And we let it run with these simplified forcing mechanisms that you have seen. And it's kind of either a 2-degree resolution, like 200 kilometer type spacing or 100 kilometer spacing. So these are kind of notations for the grid point spacing in the dynamical core. And output is collected here, velocity, surface pressure, temperature, moisture, surface fluxes, and also these tendencies. And these are our learning targets, these time variations of temperature and moisture and precipitation. And the way we do it, but it's not a unique way, we run the model for 50 years, actually, and we collect data. During that time, we have a 4-year gap, which is way too long. We don't need that. And then we have 6 years of test data, and they're totally independent. Test data and training data are no overlap. Yeah, that's important, of course. All right. One measure of accuracy here is, this is called R-square, or a coefficient of determination. Let's just keep it simple. So it kind of measures the relationship between the residuals and the variance of the data. That's just, in really, to make it simple, 1 is good. Yeah. So if this is small, that's good, because then you basically capture in your machine learning algorithm, small variations within the variance of the data. All right. Okay. Here's one first glimpse, and we are comparing the model output. This is now the time tendency of the model versus the machine learning trained algorithm, which is random forest, and the difference between the two. And there's hardly anything to see. Yeah, that's actually excellent. So here we see that the random forest is almost perfect in this configuration. It can basically predict really well. This is a random forest prediction, what the model wants. And this was a real encouraging result. And again, you can look at the performance. This R-square parameter, 1 is good, remember, and it is really, really high. Here we have a really fine scale. So 1 is this color here. It's almost everywhere 1, and a little bit of not a lot of decrease in that performance measure in this tropical area. So this is latitude and this is pressure. So it goes up here into the vertical. All right. But of course, this is maybe too optimistic. This was super simple. So let's ask a harder question. And the harder question, yeah, what happens if you go after a moist model? And this is now the second approach that I showed with condensation and surface interaction. So more processes. Yeah? Okay, we repeat kind of the same experiment. We let the model run. This is truth. And this is now, again, the tendency of temperature. We compare it against a trained random forest, and they look alike, and they are indeed very close. Not as good at the dry configuration, but very good. Yeah. So kind of the errors are on the, when kind of compared to the magnitude, they're pretty small. And that's also true for the moisture tendency, moisture variation. So here's the model, the truth. Here's the machine learning algorithm, random forest, and the differences. And again, this is very high accuracy. And if we look at, R square, then we have a mixed picture in this measure. So here's the R square for the temperature tendency. Here's an R square for the moisture tendency. And now you see that, okay, we are at times also diving down with these R square measures into the blue regime or the white regime, especially here in these upper levels. And there is basically, with this measure, very little skill, but a little bit deceiving. When I go back here, there's also very little signal up there. So it means actually that there's very little signal and there's very little variation of that signal. And that actually then leads to these degradations here of the R square. So nothing we are too concerned about. We are actually pretty encouraged about these high values. You see though that they are no longer just one. So there's now a more complex structure even in the performance here in this moist model. And it's expected because, it's just more complicated and machine learning has a harder time to learn that. All right. I want to kind of wrap up with a couple of comments also on precipitation. And the precipitation, again, this is now kind of a time mean, zonal mean, so kind of the climatology of the model, the truth, machine learning, random forest, and the differences. And this is more complicated. Also, we are integrating now all condensation rates in the vertical. So this is also very encouraging, especially when and this is another way of looking at it, if you not time average this too much, if you just look at instantaneous truth of precipitation versus machine learning estimates of precipitation, we are pretty okay following this one-to-one line. It's not perfect, you see scatter around this one-to-one line. And also there's a little bit of a flattening in the machine learning algorithm at very, very high precipitation rates, but it's extremely high, these rates. It's a lot of precipitation. So we are pretty encouraged though that we are capturing these extremes. All right, a little bit of eye candy to finish. And this is now with a neural network. So far all random forest, but another alternative is a neural network. And the eye candy here, let me start this animation. It's showing us the precipitation rate here in the model. This is truth, and then the neural network precipitation. And I let this go for maybe 10, 15 seconds, and you can kind of maybe go back and forth a little bit. It's not a perfect match, but it's a really good match between, the truth of precipitation, and then you also see these, precipitation bands here in mid latitudes, a lot of precipitation in the tropics, which is also, of course, present here in the true model one. So we are pretty encouraged about, the similarities of, the estimated or random forest precipitation, neural network in this case, neural network precipitation and the truth. And this is complicated. As you see, this is now the vertical integral of this. All right. Let me stop here with a couple of extra thoughts, and this is actually important and not so good. So there are also bad news about machine learning. Here again from the neural network. Overall, let's kind of look at the latitude, precipitation rate here. This is basically a time mean, zonal mean, profile, and you see neural network and the truth. They're a really good match in general. But when you then look at these instantaneous, this is not even instantaneous, this is even a time mean of the precipitation here in the true model, and in a neural network, you have one outlier. Let me actually highlight that. And that's, you know, the white color, and the white color is negative. And that's not good, yeah? So you don't want negative precipitation anywhere, and especially not in a mean, in a time mean. So this is a concern, and that means that neural networks, or in general, you know, all machine learning algorithms, they need to be taught physics. Yeah, we can't allow that to happen in real applications. And that's really my take-home message. Yeah, my question was, can machine learning be used as an emulator in weather climate models? Yes, we think yes. They can emulate physical parameterizations. I showed it here with very simplified processes, but more complicated ones have been shown also in the literature. They're not perfect, no. The machine learning performance, yeah, that gets challenged for more nonlinear, more complex interactions. That needs more effort, more complicated machine learning algorithms, and also more data potentially. And that's very important. We also need really smart data pre-processing choices and hyperparameter tuning. It's essential to get good performance. And I don't have time to go into this today, but maybe the bootcamp gives an opportunity. We are not claiming here we made the perfect choices for the things you saw. So there's probably ways to improve upon that. And the next step for us will be also to couple this back into an actual climate model and to see its online performance in action, not just the offline performance that we tested right now. I'm happy to entertain questions with that.
Thank you, Christian. Yeah, if there's a question, Christian, let's hear it, and then we can take a short break. So any questions? No? Okay. Well, again, thank you, Christian. It was a great talk.
All right.
And we will have a short break, and we'll reconvene at 2:30. Okay, we'll see you then. Thank you.
Right.
Hello, Ranzi.
Hi, Jonathan.
How are you?
I'm good. How are you?
Very good, thank you. So it's 2:30. So I think you're welcome to share your slides and begin your talk.
Sure. I'm glad to share. Can you see my screen now?
Yes, you can.
Okay, good afternoon, everyone. I'm an assistant professor of landscape architecture in School for Environment and Sustainability. So I'm trained as a designer for almost 10 years. So I think it's an interesting story why we apply data science to study how to plan and design. So the reason is that in SEAS, our LA program focuses on ecological design. So we really try to find some solid evidence about which built environment factors affect our natural environment, so we can improve it from our planning and design interventions. So that lies the foundation of some data-driven or statistical model. As I will talk today, the title is Interpret Important and Interaction Effects of Urban Form on Stream Water Quality using knockoffs and some iterative random forest. As an acknowledgement, this research was funded by Graham Institute of Sustainability and Huron River Watershed Council. It's our local watershed council support all the data. Professor Yang Chen helped with the algorithm design, and also research assistant Chen Zuo and Qifan Wu, Xiaohao Yang helped with the algorithm implementation. Some of them are here attending this workshop. So as a very gentle background introduction, so our domain is not as complicated as climate science or space science. So it is very straightforward linking to our everyday life, because landscape architecture, we aim to improve the quality of our environment. So this is a picture of our local Huron River watershed. Our watershed is not very clean, so there are some like phosphorus and E. coli pollutions that potentially cause the eutrophication in the Great Lake. And stormwater runoff, also known as non-pond source pollution. So it causes more than 50% of the pollutants entering the river from the non-pond sources. So our research is trying to find the source of this non-pond source pollution and try to improve those factors by our landscape design. That's the purpose. And next slide, I'll show you some framework of our research that indicate our research question and the following data-driven model. So stormwater quality is the factor of interest, which will become our dependent variable in the following analysis. So stormwater quality is affected by those purple factors, which we call intervention factors. That means we can control these factors by design. They are land use, infrastructure, impervious surface, so on and so forth. And the other factors, we call it control factors, marked in green color. So they are climate, weather, geophysical factors. We cannot control it, but we can study the interaction effects between those control factors and those intervention factors. So we can kind of infer, like, under future climate change, which variable we can control can become more important, then come up with some resilient planning and design strategies. So right here, you can see there are two boxes. One is urban form effects, one is interaction effects that become our independent variables in the coming analytical models. So here, urban form is a term you might not be familiar with. So so here we give some examples. They are kind of street layout, street surface, building height, land use pattern, so on and so forth. Okay. So here I directly took my research questions. On the left, it's our framework. So our assumption is that urban form and natural factors, they interactively affect stormwater quality. And then we have some specific research questions. First, we want to know, are urban form factors important to stormwater quality, and which urban form factors are more important? So we can naturally infer some like feature engineering or feature selection algorithm from this research question one. And for the second question, for each urban form factor, is the influence on stormwater quality positive or negative? What is the uncertainty level? So this naturally implies some regression, right? The last one, do urban form effects on stormwater quality depend on different natural conditions, such as rainfall intensity, temperature, and soil types? So this implies some interaction effects we will incorporate to our models. And then I'll talk about our two this is methodological challenge prior to our specific algorithm. Because we are kind of in the domain of landscape architecture and urban hydrology. So if you kind of familiar with urban hydrology domain, you may know the hydrological model, which are physically based, kind of a predominant approach in our discipline. But the physical hydrological model have some limitations. For example, we cannot incorporate any variable of interest if the physical mechanism is not direct. So in this case, the empirical model are more suitable for our research question because we are interested in urban form, and urban form are not represented well in the hydrological model. So that is the rationale why we apply data-driven model. And then because the relationship between urban form and water quality is apparently nonlinear, so some nonlinear models might uncover some complexity in this relationship. However, so almost all the like nonlinear model, machine learning model are kind of black box. So the interpretation power is kind of weak. So in this case, we try both linear regression and some interpretive machine learning method to make a comparison to see what is the trade-offs between the interpretive power and the predictive power. So building on that, so let me talk about our data. This is a map of our local watershed. So here is Ann Arbor and here is Detroit. From the Huron-River Watershed Council, we get the water quality data from 2003 to 2020 in more than 100 sub-watersheds. Because we have 3 pollutant indicators, total phosphorus, total suspended solid, and E. coli. So we have 3 separate independent regression models later. And these are the event size, which become our sample size in the later regression and machine learning model. Also, I want to mention here that this data structure is a clustered structure because some samples are collected within one watershed. So although the climate factors are very different, but the local land use factors are the same. So there are some clustering structure which imply Bayesian hierarchical model later. So for your information, we have more than 100 independent variables. So they include the categories of traffic and road, parcel, land use, building, land cover, soil. So these are all the factors we can manipulate in our landscape design. That's why we include all of them. And naturally, we want to select some important variables among all the 100 plus variables. And our dependent variables, as I mentioned, so we have total phosphorus, suspended solid, and E. coli separately in 3 models. So based on this data and model structure, we have 2 kind of parallel workflow because we, so it's like a trial and error. So we want to try both linear and nonlinear model. So for the linear model workflow, we first select some important features by knockoffs and lasso. We are more familiar with lasso, and knockoffs was suggested by Professor Yang. So here we make a comparison to see whether their performance are similar. And then we select some important features as the independent variable, putting into the Bayesian mixed effect regression model, and then come up with the statistical inference. So for the nonlinear models, we just lump all the features in the sign in iterative random forest. And then this algorithm identify some high order feature importance, which are so both important and stable to indicate pollutant concentrations as the label we want to predict. And then I'll first start from this linear model workflow to give you a sense of the algorithm, and then show some example results. And later I'll talk about the linear model. So for the linear model, we first use lasso regression and knockoff to select some important features. So in case you are not very familiar with lasso, I just threw out this equations here. So in your common OSL regression, we solve this, so the minimization of the least square error. And in lasso, we just plus this term as a constraint. So as a result, and our model will, so some coefficient will shrink to 0. So as this very famous illustration on the right, on the left, so the beta 2 will shrink to 0. So which optimize this, this lasso. And knockoff, you may not be very familiar with. So I'll talk a little about it. So this is what I learned from YouTube, and I think this video is very good. So I put the reference here, and also the original reference of the knockoff method is here. So the idea of knockoff is that it creates a kind of fake or very similar data structure, which have certain similar correlation structure as the existing variables, and then allow for the false discovery rate control. And the advantage is that it can achieve the false discovery rate control in a finite sample setting. And it is free of like data distribution and number of variables. So it's a more flexible algorithm than lasso, I think. So this is a figure adapted from this reference. So basically, the x-axis is the feature importance of our original data, and the y-axis is feature importance of our fixed data. So they call it x tilde. And then we set some threshold here at 1.5. It means we discard everything in the corner and only leave the rest of the points. And we definitely want the feature importance of the fixed of the knockoff to be smaller than original data, right? We don't want the feature is more important in the fixed data. So that means the denominator is actually so what we view as some truth, and then the numerator here is regarded as some false. As you can see here, so the number of points here divided by the number of points here is approximately a half, x 0.5. And also the ground truth indicated by the color. So if you count the number of the red dots divided by the number of black dots under this diagonal axis, so it's also approximately 1.5. So that's my understanding of the basic idea of knockoffs. And I think Yang may demonstrate it in the following bootcamps if you want to know some details of it. So by comparing this lasso and knockoff, we actually find the knockoffs are more robust because no matter how we set the FDR from we try many thresholds from 0.1 to 0.3, but the result is kind of stable. But in lasso, if you give different lambda, so the result will be very different. Given that we have relatively small sample size, the trend test split cannot give us very robust result. So here we consider in this case, given the small sample size, I think knockoff it's a more suitable algorithm than lasso. And here is our selected important feature, both network factors and the interaction between urban form and network factors. Well, I'm not going to talk about those domain knowledge. So, and then we so put all the important factors selected here to a regression. First, we try the mixed effect model. So you may be familiar with it because, as I mentioned, our data are very clustered. So we incorporate a random intercept here in this model. And then we use a Bayesian hierarchical model to get all the inference. I think Bayesian hierarchical model is very suitable for environmental application because oftentimes the observations are measured across space or through time. So there is an underlying spatial process, and we can draw uncertainties at different spatial and temporal scales from the Bayesian hierarchical models. And this is a famous paper of Bayesian hierarchical model application in the water quality domain. And we kind of imitate their algorithm to ours and come to these results. So we basically have different coefficients distribution of some variables selected by the knockoffs. And we can apparently know whether it is positive or negative and how significant those features are. Okay, I think I have, so my time control is not very good. Sorry about that. I'll quickly go through this semi-iterative random forest. So this is an algorithm to select the interaction effects, and the original iterative random forest can be found in this paper. So it's originally used to find the combination of genes that can explain some disease. So that's the original application setting. And then we borrow it to our model to identify the interaction effects between urban form and weather. And built on the iterative random forest, so those group of authors, they developed the signed iterative random forest. So these are some basic model ideas. So they use subsets of decision tree in random forest to discover some like mostly frequently happened combination of features. And then also they recover the sign of the features, whether it is positive and negative. And then they come up with the result. So here is the result of ours. So we discover some three-way interactions, like there are interactions between high temperature, soil group D, and low density development. So these three-way interactions is hard to found by some linear models because it's hard to like list all the combinations of the three-way factors. And this is kind of an advantage of the so-called SIRF. So there are some conclusions and also limitations. So the major limitation is that we think in the feature engineering, it's hard to tell which algorithm perform the best. So there are no like R-square things because apparently like the more features, the higher the R-square. So sometimes it's hard to tell. And also I think the interaction effects, the validity is hard to tell. So if we make some changes to the input, the output interaction effects will be sometimes quite different. So we want to find a method, maybe with the help of MIDAS, to assess the validity of the interaction effects. That's it. Yeah, thank you.
Thank you, Renzi. Right on time. So well done. So I have our next speaker, Stephen Smith. He unfortunately had an emergency that came up. We won't be able to attend today, but he did graciously record his talk. So I'm going to play that for you now, and hope that you find it illuminating. So just 1 second. Okay.
Hi, my name is Stephen Smith, and I'm a...
Oops, just 1 second. Okay, sorry. So I'll start it here. Okay.
Hi, my name is Stephen Smith, and I'm in the Department of Ecology and Evolutionary Biology. And I'd like to thank you for inviting me to this workshop. Today I'm going to talk about how my lab uses data science to address questions about evolutionary innovation plans. And I have probably too much to talk about, so I'm going to go ahead and get started. So first off, I want to orient you biologically to at least one of the groups I'm going to talk about today. So there are two plant species that live in Antarctica. One of those is the grass, and one of those is in this group called Caryophyllales. The one that's in the Caryophyllales is closely related to species of cacti, which are also in Caryophyllales. Obviously, they're a different environment in Antarctica. And those are closely related to species that are carnivorous, one of the larger carnivorous plant groups in the flowering plant lineage. And all of these are closely related to beets, which have that really striking color, which is a particular later. So my lab is interested in basically the evolution of these kinds of biological complexities and innovations. And in particular, we're interested in several phenomena. First of all, biological innovations can arise episodically. So despite the complexity, they can arise in short bursts of time close to each other. They may or may not be associated with an increase in the number of species, and they often include a really complicated set of genetic elements, so more than one gene. So for this particular workshop that's based on data science, I have a few themes. In particular, I'm going to primarily talk about our analysis of really large data sets and the development of some very simple methods to sort of analyze these. I won't go into too much detail because there's not that much time, but just as an example. Then I'll talk very briefly about a project in the lab where we're using machine learning methods to create some data sets based on herbarium specimens. And then I'll just mention extremely briefly that we're also developing some machine learning techniques to examine evolutionary processes that underlie some of the data. I would say if I had one major theme that underlies the whole talk, it's that large data sets and relatively simple methods can lead to a lot of really interesting insights. However, we need to develop tractable methods, so ones that can be computed on such large data sets because they continue to grow. Okay, so I'm going to talk a fair bit about phylogeny. So let's just let me give you my an intro to that. So humans are more closely related to chimps and bonobos than anything else. We might draw a relationship with something like this. But I think what's really important is that underlying these relationships on those lineages and nodes are population processes. There are a bunch of different processes that we'd like to understand. So we're interested in that kind of stuff. Now, phylogenies have become really common these days, really important for epidemiological things. They're used in paleontology, of course. They've been, COVID pandemic, lots of phylogeny associated with that. People get them tattooed on themselves for whatever reason. But the field of phylogenetics has developed quite a bit over the last few decades. So we're not going to talk about the origins of phylogenetics, but let's just say when I was in graduate school, I spent a lot of time sequencing a few genes for a few species to ask questions like, the honeysuckles, did they change climate tolerance when they dispersed over to North America? They did. They tended to get into warmer environments. So, a few species, few genes. People like myself back then would have contributed all of this data to a central database, and that database continues to grow, and you can extract that data, develop some methods. We've done some in the lab to make enormous trees, so you can ask totally different questions. You can say, well, is the flora of Eastern China different than Western China? And in this particular example from a few years ago, we answer this question to say that the flora of Western China tend to be more recently evolved plants than those in Eastern China. Okay, so going back to that plot, this is few gene regions for a few species just accumulating from all the researchers over the years. However, the big change that occurred after the Human Genome Project was this next generation sequencing where we could generate all of this genomic data. So this blue line is the same blue line from the previous slide, but it's completely eclipsed by this red line, which is genomic data. Now, we also, in my lab, generate genomic data. So I'll give you an example of our generation of some of this and then how we've used some simple methods that we developed to answer some interesting questions. Okay, so looking at the Caryophyllales, which I introduced in the beginning, it has several thousand species, an extreme disparity in life history and innovation. So for example, they include, as I mentioned, a lot of the carnivorous plants that people know, sundews, Venus flytraps, a lot of pitcher plants. Duplications, it turns out, genome duplications are associated not only with morphological changes, but also changes into new areas and climates. And so, at least in the Caryophyllales, they're associated with innovation. From a data science perspective, we can detect these by examining these huge data sets with diverse data types, relatively simple new methods. So there are other signatures within these data sets that we can get with these simple methods. So let's go back to the carnivores. Well, it turns out that if we looked at those individual gene trees that have these duplications, they don't all agree. Often they can disagree. So we developed a very simple method to just identify where they disagree on the tree. There's not a fancy model, anything like that, because we need to be able to analyze thousands and thousands of genes. So we do this and we ask, well, do those coincide with the areas that have the genome duplications? Here, we have a pie chart that just says, well, there are the proportion of gene trees that conflict, the proportion of gene trees that are concordant with this particular relationship, and then a proportion of gene trees that are completely uninformed. And in this case, we can see that there are particular regions of this tree that have very strong conflict in uninformative trees. So we just presume something must be happening there. Now, what could be happening could be any number of things. For example, there could just be low evolutionary signals, so there's not many changes that we can detect. There could be population processes like incomplete lineage sorting. There can be gene duplication and loss. There could be hybridization. There could be error, all this kind of stuff. We don't know. That's something that I'll mention in just a bit, but nevertheless, there's something going on. Now we can look actually across flowering plants through time and ask, well, what about the proportion of genes that conflict versus are concordant, that agree? So this is just the number of genes. And you can see that it's heterogeneous across time. So is there something going on when there's a lot of conflict going on versus when there's not? So we wanted to examine this. So conflicts are the result of evolutionary processes. So we want to understand, what are they associated with? One of the questions we thought is maybe they're associated with these major innovations. They capture population processes. Population processes are associated with innovation. Maybe they're associated. So here is that Caryophyllales tree again with the black circles corresponding to how much conflict there is. Seems like there are areas that have a lot of conflict, and maybe that is an area where there's a lot of innovation. So we ended up looking at multiple data sets, not just the Caryophyllales, but also non-flowering seed plants, ferns, another group that I work on for the Ericales, and then mammals, which I'll show you in a second. And basically these plots have conflict at the top, and then the morphological rate of evolution at the bottom. And we were just looking for whether there's correspondence. Let's just look at the Ericales, and you can see that, lo and behold, there's this spike in conflict that corresponds to a spike in morphological rate. If I go to the next slide, you can see in mammals, a spike in conflict and a spike in morphological rate. Spike in conflict is a different data set, and a spike in morphological rate. So in each of these cases, we're seeing that there are correspondence between conflict and the morphological rate of evolution. So that's interesting. So if we look at, I mentioned another group that we work on in the lab is the Ericales. Here, that same pie chart thing, and you can kind of visually see with your eyes that backbone is really conflicting. So we haven't, we just showed that it has a spike in morphological rate. Well, it turns out that it also has a whole genome duplication associated with that. So there's a whole genome duplication, a spike in conflict, and a spike in morphological rate. So that's interesting. So there's one other aspect of this that we wanted to analyze, and that's the models of molecular evolution. So these underlie all of the analyses that we're doing. And it's just one other element that we could ask questions about. So we wanted to say, well, what if we allowed the model of molecular evolution to vary across the tree? So certain parts of the tree have different models of molecular evolution than other parts of the tree. This is something that we developed in the programming language Go and C in a couple of packages. And we just wanted to develop a simple information theoretic measure to detect where these shifts might occur. So here's an example of a single gene where we're looking across all of land plants and we're asking about shifts in these models. And we see several of them. The colors correspond to that in the tree on the left. And then the bars there are the actual nucleotide composition, the proportion of A's, C's, G's, and P's that we're detecting the differences. And so we detect these differences across vascular plants and land plants. And so I'll summarize that in just a second. We also noticed that there are differences between amino acids and DNA. So these are the exact same gene, but one is amino acid alignment, and the other is DNA alignment on the right. So we get differences between those. We summarize this across all of land plants, and you can see the red, the colors there correspond to how many shifts we find between all the genes that we analyze. And you can see areas where there's a lot of red. We're not going to belabor this point. Instead, I just want to focus on the idea that when we look at shifts in different genes, so on the left side, we have 4 different nucleotide genes. And on the right, we have 4 different amino acid genes, just taking a set out of our larger set. And it turns out that the shifts in each gene tend to be in the same direction. So for example, as plants have moved onto land, they tend to get more A's and T's than C's and G's. And that's reflected in the amino acid data set as well. It seems to primarily be a nucleotide pattern. And so here you can see, for example, that blue, there are seed plants and land plants over here, and they're shifting toward this A and T. That's basically what that's showing there. And so this is basically what we've found, is that as plants move to land, there tend to be shifts in this nucleotide composition. This is reflected in amino acids, and it's probably reflecting lower population size, so this population processes, and slower generation time, because this A and T pattern tends to be associated with mutational bias, which might be the result of drift from low population size, as opposed to if they had GC bias, which would be more meiosis. These also tend to be across the genome, while there are within gene patterns. Okay, well, we'd like to compare this to morphology. I already mentioned that we looked at conflict and genome duplications with morphology. However, there's not much available. So this is the other kind of data science aspect of the lab that I'll just race through, which is using machine learning to try and increase the amount of data that we can get off of morphology. So this is using herbarium specimens that come from the museum. And the idea is to try and use semantic segmentation to detect leaves and other objects so that we can get measurements. So we would have, all of these specimens. There's ground truthing involved. There's, we take these images and then try and classify leaves and then get data from those so that we can eventually use those for analyses. So there are several different algorithms that, primarily grad student in my lab, Will Weaver, is working on. So one is a program called Leaf Machine that he uses to basically outline leaves and grab data from those. There are other methods that we can use, especially if we can get better data, like cleared leaves, where you can take away the actual green portion and just be left with all the veins, or X-ray leaves. Nevertheless, we've been using these methods to do some test data sets on plant families. This is just an example of particular leaf set from this group called the Acacia that we've been working on. And we have some general success stories where we're able to if we have good images, detect and extract these data, but also some challenges, which is that we have to do relatively specific models for these machine learning techniques. So for example, if we train on all these Icacinaceae data, those models that we've developed are not applicable really to other groups. So this is an example where we've taken those Icacinaceae data and applied them to a totally different plant family, in this case, the one that contains the oaks, and the results are not very good. So this is an ongoing project in the lab where we're at the moment spanning out to several data sets, some within species, between closely related species, and broadly across flowering plants. With the lesson from this first pilot study of the limitations of the quality of the images and how much time it takes to ground truth. Nevertheless, it's promising, and over the next few months, we're going to be generating some of these data to basically add morphological data to all the stuff that we just talked about. There's one other machine learning project that's in the lab, which is basically trying to categorize evolutionary processes using GAPC. This is, a summary statistic approach, basically a lot of simulation, and then try to identify the processes that underlie our fees based on the shapes of the trees and other summary statistics. This is something that within the lab with some collaborators we've experimented on before to detect processes like hybridization or population processes like incomplete lineage sorting, and it's something that we're expanding on. So recently we just submitted a grant based on some pilot work and a pilot grant from MICD, where we're planning on combining a lot of this stuff together, basically. So generating a lot more morphological data based on the machine learning algorithm I just mentioned, adding that to all this phylogenetic data and those methods, and for DAPC methods for identifying processes that may be underlying those, so that we can, ultimately infer a more rich evolutionary inference of the history of the emergence of evolutionary innovation. Because all of this includes a lot of interaction between machine learning techniques and other sort of data science and biological techniques, we're also developing some interesting teaching activities that we can spread between a few universities. Okay, so just to wrap up here, went a little long, sorry about that, but basically what I was trying to demonstrate here is through a biological example, the large data sets with relatively simple methods can lead to a lot of really interesting insights, but we need to develop tractable methods. And this is primarily because we're dealing with such large data sets. So here I tried to show that evolutionary events leave their signature in genomes in the form of extensive conflict. These may or may not be preceded by morphological innovations. In plants, those innovations are associated with gene and genome duplications. And then these molecular models also contain the signature of population processes. So this is all just taking all of this rich data resources and just analyzing as much heterogeneity as we can have. All right, well, I'd like to thank my funding sources and collaborators here, and also my lab that's been involved in all this project. And thank you.
Okay, thank you. So I believe Stillian, you're next. Please share your screen when you're ready. I can see your slides.
Hi, thank you so much for the opportunity. I've enjoyed tremendously so many great talks, and I've been fascinated by the science that people manage. Do you hear me well? Fascinated by the science that people manage to do using modern machine learning techniques. I'm a bit of a novice, and I will talk about more from statistical standpoint about the spatio-temporal functional data. And hopefully this may inspire some collaboration in the future. So first of all, let me introduce the team. So the driving force behind the work that I'm going to present is really the students, and this is Drew Yarger's work. Moritz and Drew have been working closely. I will present a little bit of their work at the very end. More theoretical work in our group was done with these two fellows, Jingxi, who's now at Airbnb, and Rafael Kertsukas. The leader of our group is Professor Tailan Xing. He's an expert in functional data analysis. And of course, we're very grateful to them. So without further ado, well, I know there's very little time at the end to provide references. So I'd like to start with the references. So Tailan, the leader of our group, he's very well-known expert on functional data analysis, mostly the theoretical foundations of the subject. So he wrote this this book, which is our Bible. This is the first thing. But we look at other people's Bibles as well. This is the French school. I'm not sure I pronounced the name correctly. Chiles and Delfner. This is a great book. The book is dedicated to Georges Materon, who's the one of the founding fathers of geostatistics. Another excellent book we look at all the time is Mike Stein's book, Interpolation of Spatial Data. So here is just a sample of some of the things we do. We've done some theoretical work with Jingqi, basically on stochastic process models that take values. The values of these stochastic processes are functions. Okay, so basically that's the common theme behind our research. That's what motivates us. I'll come back to this point in a minute. We've done work on the spectral density estimation, but in the case when your process takes values in a function space. So what you really measure are functions, essentially, theoretically. Okay. Today I'm going to talk about methodological work, largely, almost entirely. This is a work of Drew Yarger, who's graduating this year. And it's a functional data approach to the Argo data. Argo is a fascinating, fascinating oceanographic data set. This paper appeared in the Annals of Applied Statistics. And then, if time permits, I will briefly mention what Moritz and Yarger and Moritz and Drew have been doing, extending this work again with applications to prediction of oxygen in the Southern Ocean. So before I begin, I will give some context, some formulas, some notions from functional data analysis. So basically, for us, the data are random functions. Okay. So there are these abstract object x1, x2 that take values in some space of functions. You can think of this as functions f, let's say defined on the interval 0, 1, or they could be defined on in a more complicated part of the Euclidean, multidimensional Euclidean space, such that f has some smoothness. Okay, f, for example, in this case, f has q derivatives, and also this integral of the squared qth order derivative of f is fine. Okay, but in reality, you never really observe functions. You observe sample functions. So in reality, you observe this xij. So sample I involves ni measurements at of these functions indexed by pij. But and also you don't really observe the functions. You observe them with some typically modeled as additive measurement error epsilon, given here in red. So what we have in reality, sort of the left-hand side, these challenging, sparsely sampled data. So functions are never really observed in their entirety. They may be irregularly sampled. So different sample points, so to speak, different xi's can be sampled a very different set of locations or arguments in the function. And of course, measurement error is present. So how to square all this? So in all this, in this context, a tremendous amount of literature and statistics has been developed in addressing some basic, some fundamental problems. Here I'm just going to mention a couple, but there are many more that have been addressed in a very theoretically satisfying manner. So one basic problem is you want to estimate the functional mean. So imagine that these are independent observations, okay? But in reality, of course, you have dependence, and that's what we will model. So if you have independent observations, for example, you want to estimate this functional mean. This mu here is not scalar, not even a vector, it's entire function that belongs to this function space H. Okay. Or you could, or another more complicated problem would be to estimate the covariance operator, which is now something that lives in this outer product space, in this tensor product space. Okay. Of course, how to do that? I mean, the workhorse is essentially smoothing techniques. Okay, so the basic idea is you estimate this mu with some sort of penalized least squares approach. Okay, so I'm just sketching one of them. This is there are many more. So for example, you seek so your estimate of your functional mean, for example, is a function mu that minimizes this objective function. So this objective function sort of balances how well you fit the data. So this is the first term versus how the complexity of the model, which is well, it's penalized by some sort of measure of roughness. Okay, so that's just a sketch of some ideas. And I mean, of course, in practice, you have all kinds of issues of how do you represent these functions. You cannot really store a function in a computer. You store some sort of representation, approximation of that function. But let me get to the data, the more interesting part. So the Argo project is a multinational effort. I don't know. I mean, the audience doesn't like to ask questions, but is the audience familiar with the Argo project?
I would assume not.
No. Okay. So it's worth checking it out. It's absolutely fascinating, multinational effort. It started in 2000. And so what's the goal of this project? Oceanographers want to monitor basically all open oceans. And their goal was to place a float, which is an autonomous device, in roughly each 3x3 degree square in all open oceans. So this goal was achieved in 2007. So currently there are about 4,000 floats that are autonomously collecting temperature and salinity data. And in fact, there are much more advanced floats, but a lot fewer that collect also oxygen measurements, nitrates, and so on in different parts of the ocean. So they automatically submerge to a certain depth, and as they raise to the surface, they collect temperature and salinity data. And once they're on the surface, they beam these data through satellite internet, and this is being recorded in a data processing centers. So we thus obtain basically so-called profiles, which are definitely of very functional nature. You can imagine these temperature and salinity being functions of pressure. Pressure, by the way, in decibars is in basically one-to-one correspondence with meters. So if you go down by 1 meter, the pressure increases by 1 decibar. So each profile has its timestamp, longitude, latitude, and an array of temperature measurements and salinity measurements, and of course, the corresponding pressure levels at which these were taken. Okay. As you can imagine, all these challenges of irregularly sampled data, space-time data come in. So this is not a very, very large data set. You can fit on pretty much anybody's PC these days, but it's quite complex. These data are very professionally handled and by the community, and many quality control issues, data management issues are very professionally addressed. So here's just an illustration of the Argo project. It has been a treasure trove for oceanography and climate science. Literally many thousands of papers have been written by the oceanographic community using the Argo data. That's a snapshot taken from their website at Scripps. Currently, there are about 4,000 autonomous floats represented by the dots here. And as you can see, they're sort of randomly, uniformly spread out in all open oceans. So on the right-hand side, we have an illustration of a particular cycle of measurements that produces one profile. So the float submerges, and it stays at its parking depth, which is about 1,000 meters, for 10 days or so. Then goes down to 2,000 meters, and then as it rises, it collects data, beams it to the data processing center, and repeats. There are all kinds of reasons for these choices. Why does it park at 1,000 meters and so on? Why does it go to 2,000 meters? I don't understand them all. So at the end of the day, we have fascinating data. Anybody can download it and do stuff with it. So where does statistics come in? So some challenges and opportunities, sort of in this context, the way I understand them. These data are fundamental in trying to map the ocean heat content. We managed to assess using functional data methodology, the so-called mixed layer depth, which is another feature. Basically, there is a certain layer, sort of its thickness depends on where you measure it, where on Earth you are, and what the season is. But a certain layer where the ocean water can mix freely, so to speak. So this is very important to understand the thickness, the size of this mixed layer depth. The thermohaline circulation, the oxygen concentration, and so on. So I truly don't understand the science behind these things. But what motivated us to work on these kinds of problems is that I think we had something to contribute. So answering these questions require estimation of a function, and in fact over an entire continuous pressure range. So the data are sparse in space and time. They're not so sparse in pressure, but they're quite sparse in space and time. So how to interpolate across space and time in a meaningful way is important. You have to have a good model to do that in a principled way. So, of course, you have like this technicality, different float sample at different pressure levels in principle. So the existing approaches, most of the existing approaches were one pressure level at a time and for a fixed P. So we felt like statistically that's not satisfying. So we developed a functional data framework where we holistically view temperature and salinity as functions indexed by space and time. We model them and we estimate their characteristics and predict various things. So I'm running out of time, but Drew has been amazing. Maybe it's worth mentioning Shiny. I'm happy to share these slides, by the way, but in statistics, you cannot click on this. Hang on. How can I share another screen?
You should be able to stop and share your entire screen if you'd like.
Yeah. Let me just switch to that. So that's the Shiny, one of the many Shiny apps that Drew has written. This is an interactive. It doesn't do heavy duty computing, but it does decent amount of computing. So you could click on anywhere here in the map. So these are all, as you can see, bells and whistles. These are our parameters that govern our penalty. You can estimate, let's say, the mean field of temperature or salinity, and so on. So in about 30 seconds or 20 seconds, you'll get that. We could be more efficient. But here I just wanted to advertise not only sort of the power of high performance computing, but a little bit of an element that you could put computing on the fingertips of scientists. So Shiny has been fascinating. Are we there yet? There you go. So for example, here in this, from what I understand, is it like the hurricane forming region or not? You have an estimate of the mean curve of temperature. So here on the x-axis you have temperature, on the y-axis you have pressure in decibars, and this is how they display them in oceanography. Somehow the axis is flipped, okay? But it's also natural. So I could spend a lot of time on that, but I'd better move on. So I wanted to try to excite you about the functional data approach. So, for example, what does it give us? By viewing things, by viewing the temperature and the salinity as function objects, we can naturally estimate in one shot, for example, the expected temperature, the expectation of the temperature as a function of the location and the time. We can also estimate these so-called derivatives, Gateau derivatives, in a way that give you an idea of how does the temperature profile change as we move from east to west or from north to south or over time. One can account for seasonality and so on. So these kinds of objects are not accessible by looking at things one pressure level at a time. So this is, I think, a success story of applying mathematics and statistics to a complicated data set. This is an example. I'm really fond of the plot on the right-hand side. The plot on the left-hand side is also great, but it's you need to think a lot. So on the right-hand side, it's the gradient vector of salinity. And here you can see the outlines of Africa, North Africa. Here, this is, I think this is Portugal, and this is Spain here. So you see this, by the way, this is estimated at the surface or just about 10 meters below the surface. And you could see how the gradient, it's pointing, basically identifies the flow of salty water from the Mediterranean Sea into, which is a little saltier than the Atlantic. We were fascinated. We learned by fitting the model. We didn't know much oceanography, but you know, once you estimate the model, you see these features. So I think I'm running out of time. I have a lot more to say. Let me end with a picture about ocean heat content. So Drew has developed a framework that models not just the mean, but of course the covariance structure, the dependence between temperature and salinity, which allows us to provide, for example, this picture, which is estimates of ocean heat content in a very fine 1 by 1 degree grid. Of course, we could do it. In fact, it's a matter of computation, arbitrarily, on an arbitrarily fine grid. And the right-hand side provides estimates of the certainty of the ocean heat content. So that's not quite ocean heat content on the left. It's the anomaly in ocean heat content, which is what's typically reported. This agrees with the NOAA estimates, but I guess it has a bit more detail. And that's our latest project. This is work in progress with Drew and Moritz. An important problem in oceanography is estimating oxygen, but Argo floats that can estimate oxygen are a lot more expensive and far fewer, and you can tell here. This, by the way, the globe is centered so that you are looking straight at Antarctica. And you see at the top plot, you have far fewer of these biogeochemical floats, BGC floats, that are capable of estimating oxygen. And these on the bottom are all the floats that can estimate temperature and salinity. So by building a joint model that captures the behavior, the joint behavior of temperature, salinity, and oxygen, Moritz and Drew managed to predict oxygen at places you don't have biogeochemical floats, and that's the picture. And I think that's very important scientifically. Thank you so much for your attention. Happy to take any questions when the time comes.
Thank you, Julian. If there's any questions now, we're happy to take one. Otherwise, we can have a discussion after the last presentation. So, any questions? Okay, well, thank you very much, Dylan. This concludes the sort of success story section, all these awesome applications of computational and data science methods to environmental science. So now I'm just going to sort of end with a description of the next stages of the training program, and then we'll have time for sort of question and answers about the training program itself, and then we'll have a sort of open discussion amongst the attendees and the presenters on any topics that you wish to discuss. So just give me a second, I'll share my screen. Okay. All right, so as I mentioned earlier, the training program is 3 parts. This is the workshop, of course. And so, oops, there we go. So what comes after this? So after this is the boot camp, which has been alluded to. I should mention that we are planning on having a sort of very modest fee associated with the boot camp, roughly around $100. So I think for all attendees, I don't think it's a particularly onerous ask, but that's the current plan for that. So it'll just be $100 fee for people to register for the boot camp. And so it's going to be 5 days, again, from May 16th through 20th. And this is going to provide you an overview of the schedule of the topics and so forth that are we're going to cover. Again, these are maybe subject to change based upon availability and so forth, but sorry, my slides were not advancing. Okay, so in the first day, we're going to have, of course, an introduction to the program. We will cover some basic math that you may need, just a refresher. Generally, again, this is not meant to give you a comprehensive understanding of linear algebra and optimization and so forth, but we will touch on some of the aspects of math that you may need to understand some of the models, and of course we will try to integrate these more in context as you learn models and you need a certain certain understanding of some aspect of linear algebra or optimization. We will try to provide those in context, so just so you can understand the particular models and so forth. In general, the format of the bootcamp will be, we'll have roughly an hour and a half sessions, followed by breaks in between, with some kind of practical sessions in the afternoon. In the first day, we'll cover some, basic notions which you've already heard a number of times in the talks today. So supervised learning, where we have some labels associated with it. Unsupervised learning, where we are looking to determine groups of data points based upon similarity. And we will cover in the first day also the basics of programming in Python. And we'll have also some of the models which you most likely will be many of you are familiar with, like linear regression and least squares, things like that. So the first day will be sort of a introduction to programming, introduction to machine learning, and some of the basic methods. For Tuesday, we're going to continue with other methods in machine learning. So naive Bayes is another simple method that despite its simplicity, it's actually still very useful at times. We'll also cover some of the main processing steps or things associated with machine learning. So it isn't just creating models. It's we have some kind of data processing. We extract features, information which is relevant to the task at hand. And as Renzi mentioned, like looking at trying to pick features and find which ones are meaningful. This is something that is a critical step in machine learning. Also, we'll cover principal component analysis, which is one way of doing dimensionality reduction. The idea that we're taking a lot of features and we may have too many for the number of data points or for the model we wish to use. And this is one means by which we can take the number of inputs and sort of reduce them down to something more manageable. We'll look at assessments of models. So I think others mentioned that there isn't just one way to measure the performance of the model, depending upon what you're wishing to achieve, what's a task that you're looking to have your model achieve. It's prediction, it's classification, clustering. There's different methods for quantifying its performance, calculating its performance. There are also strategies for reducing bias, and one method by doing that is known as cross-validation. And again, this is ways in which you can partition your data and train models on your data so that you hopefully get a more robust model that will generalize well. It will perform well on data which has not been seen. There will be additional programming on Tuesday. And we will have on Tuesday, the first session, which will be essentially extended versions of the talks that you've seen today. So hopefully we'll have some of the speakers back for the boot camp. And so they will have then an hour and a half to sort of really get into sort of the details of how they use in their domain used machine learning or data science techniques to try to solve the problem. So again, these are sort of be some kinds of, you can think of them as case studies that this will enable the participants to be able to sort of look at a real world problem and how it was solved, using machine learning techniques. We'll end Tuesday with a description of artificial neural networks, which are, again, you've seen some examples used today, and these are sort of the precursors to what people tend to refer to as deep learning today, but they in many ways are quite similar. But these are the initial ones to start with. So for Wednesday, we will go over decision trees. There's a particular algorithm called CART. And again, decision trees can be used for both classification and regression. You heard many times today about random forests, and this is an ensemble method. The idea here is that we take essentially decision trees, and we create a whole bunch of them, which is why rather than having a tree, it's a forest. It's a collection of trees, and we try to use each of these to help us tell us about some portion of the data, some portion of the features, and make a consensus estimate of either. Again, this could be used for regression, where we want a value, we want to predict a value, or it could be used for classification, where we want to know, is this, a cat or dog or anything else that you want to know. So we'll do another programming session, and again, we'll have some experience with using some basic artificial neural networks, random forests, and both for classification and regression. We'll have a second session for seeing an application of machine learning and data science, environmental science. And then we have, I had asked, or the group had asked all participants to sort of indicate their preferences for some topics that may be particularly relevant to those working in environmental science. And so one of the top, responses was anomaly detection or rare event detection. So we're planning on having a session on that and learning about those kinds of techniques for the attendees. So for Thursday, we will cover support vector machines. And despite the name, it's essentially a way of finding, some way of separating points in a higher dimensional space. You find some kind of effectively, some linear plane, hyperplane that is separating points. But they have some nice analytical properties, and again, they are still widely used, even if they're a bit of an older model. We'll have some experience with that in Python. And then we will have a couple of sessions on deep learning. So we're going to cover the basics of deep learning, what deep learning means, when to use it, when not to use it, how to make sure it's used appropriately. We'll probably talk about both convolutional neural networks as well as perhaps some sequential models like LSTM, long short-term memory networks. We'll have some experience doing that in Python. And then for the last day, we'll have the other special topic, which was the second most popular choice by the attendees, and that was equation and model discovery. Again, I think that's particularly applicable in many domains. You see that in Stilian or Christian's talks, that you have physical models that have some kind of equations, but there are potential ways to these are still approximations. So there's potential ways of either improving those models using some machine learning techniques, or if you have data which is being collected from all these sensor networks all around the globe, potentially discovering new equations or improved equations to aid in your modeling. So we'll cover some of that. We'll have a few additional sessions on learning about applications of machine learning to environmental science. We'd like to discuss some sort of general guidelines. So after seeing all of these different techniques and methodologies and so forth, try to provide some overview of, when you have a new problem, which techniques should you consider? what are the considerations in terms of data? Some of the things that Yang mentioned about knowing how the data was generated and all that whole life cycle or pipeline of creating a model from start to finish. We'll hopefully discuss then, and then we'll end with just again a broad discussion about answering questions about anything that was discussed, and then the plans for the follow-up sessions. Are there any questions about the schedule before I move on from anyone? Okay. So one thing I should mention is that this is a week-long boot camp, so it is going to take place in May, so it's outside of the primary semesters, winter and fall, but it may be a large time commitment, or at the same time, as I mentioned earlier, it may be the case that since this is just an introduction, you may want something more. So I want to offer a couple alternative resources that in one paper, one will give more information but also more commitment, and maybe one which might be less. So there is a Master's of Applied Data Science that the School of Information administers, and this is a degree program, of course. I believe there are some discounts for U of M faculty and staff, but there's a whole bunch of other reductions that they have. So. But this is a full program. So this is a year full time, or it could be done in 2 or 3 years. And it will cover all the things that we are going to cover in the boot camp, and then some, and lots of things that we're also not really going to focus on. So some of the data collection and processing things that Yang talked about, natural language processing, network analysis, which people use all the time for analyzing social media and other kinds of social networks. So it is a very comprehensive program. And this could be something that could complement what you learn in bootcamp. It's not mutually exclusive. You could get an introduction, and if you feel I want to continue, you can consider this program. For more kind of ad hoc or individual lessons, CSCAR has a great set of workshops that they run, and these are usually available via Zoom, and they have them all throughout the year. So I would urge you to take a look at those and see if there's any workshops that interest you, and you can register for those, and those are free as far as I know. And they also do some things that they will have that we will probably cover less of in bootcamp, of course, is more sort of standard statistical techniques. So if you still would like to learn about sort of straightforward statistical methods, they will cover that. And my experience with them, they are, again, they tend to be really great workshops. So so that is the end of the second phase of the training. The last part is these follow-up sessions. Okay, and so the follow-up meetings we're planning on having 2, one of each semester of next year. And in the workshops, we want to have opportunities for people who went through the boot camp and hopefully then gained the motivation and experience to do some of these, apply these techniques to their own work. We want them to present and be able to share what they've learned, what they've done, and also, hopefully, develop additional collaborations and connections between both, computational data science methodologists and as well as domain experts. I think, as Xiang and many others mentioned, David and others, really this is an interdisciplinary space, and you really need people who are truly understand the main problems. You need people who can help analyze, again, deal with these incredibly large data sets, hundreds of terabytes, petabytes of data, and all the complications of trying to run, how do you get this, your models and algorithms to run on these complex or large data sets, and again, having people who have the background information and how to understand the techniques. So it really is an interdisciplinary effort, and we're hoping that these, through the bootcamp and the workshop, and then these follow-up meetings, that we can really foster these collaborations. And we also like to have, we're hoping that we can develop, in addition to just research collaborations, peer-to-peer support network. We want people to be able to learn about how you solve certain kind of common challenges. You can have best practices. Again, what's the best way of dealing with this, ingesting this data? How should I do my hyperparameter optimization? Maybe you use a package like Chirper that Christian mentioned. So there are going to be a body of knowledge that we hope we will develop collectively and together that we can then share with one another. And what we also like to have is, again, what we're hoping as part of MIDAS, our mission is to help, catalyze research on campus. And so we're also hoping that we can provide guidance on how to take, sort of help shape up ideas you have, but maybe applying data science to one of your applications. And we're your research questions, and then we're hoping that we can help you, shape that so that you can go out and potentially put that into a grant and have success in getting grant proposals that utilize data science. So that will be the focus of the follow-up meetings. And at this point, I'd just like to stop and have anyone ask questions about the training program, and then from there we'll have some time for this, and after that we can talk about some of the presentations and so forth. So please feel free to ask any questions that you might have. Or any comments.
So I have just a question about the boot camp. As far as materials that are provided, is it just PowerPoint slides, or will there be some other supplemental materials, for example, samples of code and stuff like that we can take with us?
Oh, yes. Yeah. So at least, when we did this previously for the biomedical bootcamp, we had both slides as well as Jupyter notebooks in which, all the participants, had a copy of that code and were able to then take that and modify it as you see fit. So great question.
Cool. Thank you.
You're welcome.
Hi, Jonathan. This is
Hello.
Rindy. I would like to know, is there any link to register for the bootcamp? If there is, can you provide in the chat? I
Sure.
can send around.
We haven't created the registration link, but we will do so, shortly after the workshop. So.
Okay, sounds good.
Yes. So just so you know, there's a website on the MIDAS site that went out with our announcements, and it's also currently on. Actually, let me stop sharing. I should be able to show you just so you know. Let's go here. Let's see. Okay. Oops. Not sure if you can see this. Let me try it again. Okay. So this is the MIDAS website, midasumich.edu. And so usually on the training, we have a workshop section. And so you can see that here's the program for environmental scientists. So we will be updating the information here. Right now, the workshop is scheduled or made prominent on top, but this will be reduced, and we will put all the information about the bootcamp, including the schedule and so forth here. We will also announce it via the MIDAS newsletter. So again, if you're not signed up, I encourage you to do so, and you can do so on our website. And this will also be where the registration link will be.
Jonathan, this is Lindsay again.
Yes.
Yeah, I want to ask, because this is a weekly schedule, so we may not be able to attend at some date. So is there a pre-record video available or something?
I'm sorry, is there what?
Watch later? Is there some videos we can watch later if we cannot attend the bootcamp on some days?
I don't know if we are planning on recording the whole thing. I can't. James, do you recall what we did for the biomedical bootcamp?
Yeah, so we did record the entire biomedical bootcamp and broke that down into recordings on a day-by-day kind of basis. So those should be available.
Excellent. All right. Thank you.
Okay, thank you.
What other questions do people have?
Hi, this is Andre.
Hi, Andre.
So, and I apologize if this was covered earlier. We're doing our grad recruitment, so I've kind of been jumping in and out. But for the boot camp,
Yes.
will there be kind of a standard data set from which everyone will work, or should we come in kind of with our own data and that's what we'll just kind of work with the entire week?
And we will have data sets that we will provide as part of the labs and so
For
forth.
sure.
So yes. Good question. Any other questions? Well, I know that some of our speakers will be coming back at 4 to have the open discussion. So if there are no further questions right now, perhaps we can just take a short break and then we can reconvene at 4 and then we can continue to discuss the discussion about some of the topics presented today. Again, if there are any other questions that arise during that time, you're welcome to ask Yang or myself about them. So, all right. So hopefully, I hope that you stick around to when our speakers rejoin. Okay, so see you in a few minutes. Well, while we're waiting for hopefully some people to return, I was wondering if some of the few remaining attendees, Kathleen or Darina, Ming Xiao, would you like to introduce yourselves, why you're interested in, coming to the workshop or potentially the boot camp?
Hi, Jonathan. Is there any cost of the boot camp? I missed that information.
Yeah, so we're planning on having it be just $100.
$100.
It's
Okay.
so for a week. I mean, we think it's pretty modest, but we had a number of many more people sign up last time, even faculty, in particular faculty, for the biomedical bootcamp who did not wind up coming. So, we just like to have a small incentive, or disincentive to sign up and not attend. So again, I don't think that will be a major barrier for anyone. If it is, it's something that we can discuss. But yeah.
Okay, then I'll ask my research admin whether this cost can be reimbursed some way, because
Sure.
I think this skill set is useful for students to do research projects. So I'm going to ask that.
Great. Well, I think we can maybe wait another minute or so if others don't come back, and if there's no one wishing to have any discussions, then I think we can end early. So.
Yeah, I think that's just the nature of the Zoom networking. People are not going to speak up because it's like you're put on a platform.
I understand. So. Okay. Well, I guess thank you very much, Yang. That your talk was great, and Runcie as well. Excellent. I really appreciate it. And James, thank you for staying on for support. And I hope that we'll get a lot of registrants for the bootcamp. So.
Thanks for
organizing. Yeah, I think you need to advertise that to different departments.
Yes, I think so. All right. Thank you, everyone.
Thank you.
Take care.
Thanks, everyone. Bye-bye.